symmetric matrix. T. Krishnakumar is a director, Rockwell Analytics, USA. His topic of presentation is Probabilistic Foundation of Econometrics, Dr. C.R. Rao's contribution. To chair this session, we have with us Professor Steve Kirkland, Professor and Head, Department of Mathematics, University of Manitoba, Canada. Kindly take over, sir.
So thanks very much. Just like to welcome everybody to the session and to say, of course, good morning to you all. It is 6:30 in the morning here in Winnipeg, Canada, and also in Regina, Saskatchewan, where Sean Fallot is speaking from, and also in Iowa, where T. Krishna Kumar is speaking from. So. Sean, as already mentioned, is a professor in the Department of Mathematics at the University of Regina. He's also a friend and a collaborator of mine, and he's going to speak to us this morning on almost principal minors of symmetric matrix. Sean.
It's my pleasure to be here today to talk at this very interesting conference. The title of my talk is on almost principal minors of symmetric matrices, a topic which I'm very interested in. I know that lots of folks know about principal minors and principal submatrices, but my plan is to take it a little bit further to another class of important submatrices. So the outline for my talk is presented here. It is rather long, the outline, but I promise you that I don't have a lot of slides here for each section. So the plan is to introduce the topic to you, provide a little bit of sense of
I'm not hearing anything.
Sir, please excuse us. I think we have some small technical glitch. We are looking into it. We'll be there in just a couple of minutes.
diagonal of the original matrix. And instead of designating it A alpha alpha, I'll simply shorten it to A bracket alpha for brevity's sake. Now, once you have squares, it's my pleasure to be here today to talk at this very interesting conference.
Sorry for the technical glitch, whatever happened so far. We are very sorry for the inconvenience caused. We are replaying the video which has been given by Professor Sean Follett. Thank you.
It's my pleasure to be here today to talk at this very interesting conference. The title of my talk is on almost principal minors of symmetric matrices, a topic which I'm very interested in. I know that lots of folks know about principal minors and principal submatrices, but my plan is to take it a little bit further to another class of important submatrices. So the outline for my talk is presented here. It is rather long, the outline, but I promise you that I don't have a lot of slides here for each section. So the plan is to introduce the topic to you, provide a little bit of sense of motivation, and then take you through a little bit of the history of how we arrived to this study of almost principal submatrices. And that'll be the last two topics, topics 4 and 5, where I hope I can at least give you some insights into sort of how we're thinking about this project. So beginning with the background, so just to make sure that we understand some of the notation that I'm familiar with and hopefully will be familiar to you folks. So all the matrices in this presentation will be square n by n matrices, and I denote that by m sub n. And alpha and beta will typically denote two subsets from the set of integers 1 to n. Once you have selected two subsets alpha and beta, then this notation here, A bracket alpha comma beta, signifies the submatrix of the matrix A, where you choose rows alpha and you choose columns beta, and then you represent that submatrix as follows. And of course, you preserve the natural order of alpha and beta, not to mix up the orderings of those sets. If alpha and beta happen to be the same or coincide, then what we have is what's called a principal submatrix, so one that respects the main diagonal of the original matrix. And instead of designating it A alpha alpha, I'll simply shorten it to A bracket alpha for brevity's sake. Now, once you have square submatrices, obviously the determinant is an important factor. And so when you take the determinant of a submatrix, and in this case I've signified a principal submatrix, you refer to that as a principal minor. So the term minor refers to a determinant of some square submatrix. And in this case, I've designated a principal minor. Of course, everyone understands that the rank is an important quantity associated with a matrix. And here I'll just refer to it as the size of the largest invertible submatrix, since I'm speaking about submatrices in this lecture. Of course, rank is defined in many ways, and this is just one way to define it. Now, when you talk about symmetric matrices, or more generally Hermitian matrices over the complex numbers, an extremely important, basic, but a really important fact arises. And as I defined above, the rank is the size of the largest invertible submatrix. But it turns out for symmetric matrices, you actually don't have to choose arbitrary submatrices. You can actually just study the principal ones. And so you simply look at all the principal submatrices. Okay, and there's a lot of them, but you just look at all the principal submatrices and you look for the largest invertible principal submatrix. And that happens to also coincide with the rank. I mean, that's not obvious from the definition, but it turns out to be a fact for symmetric matrices. And it turns out to be, that's kind of an important fact that's led to a lot of, it's a lot of the reasons why there's a lot of interesting properties associated with symmetric or Hermitian matrices. And in my talk today, I will concentrate with real matrices that are symmetric. So this fact will indeed arise. Now, I've become very interested in the world of what's called inverse problems associated with matrix theory. And inverse problems are just, power set of n. Okay, so suppose I hand you a vector of length 2n, and I call that vector u, a vector of numbers. And I ask you, okay, suppose those numbers represent all of the principal minors of a potential matrix, n by n matrix. Could you find that matrix? And that's what the principal minor assignment problem is. I'll hand you all the minors, you feed me back the matrix. And this problem is really hard. As I said, it's unresolved. There are various, proposed and sort of ideas of solution. And Luke at the University of Auburn has proposed what I'll refer to as a set theoretic resolution. It's very interesting, the work he's done. It's not what I want to talk about today. And so I've just listed, no disrespect to Luke, I've just listed some keywords that he uses in order to sort of get after this problem. And it's not surprising that these kinds of, Schur modules and varieties arise, because that's exactly what's happening. An equation proposes surprise arises. But that's kind of the motivation, I would say. The principal minor assignment problem is motivation for me. So instead of solving the principal minor problem, which I'm not going to do, we looked at some sort of variations of it. And so we defined something called the enhanced principal rank characteristic sequence. And so rather than saying, suppose I hand you all of the values of all the principal minors and you find the matrix, we sort of simplified that problem and looked at a different one. And in this case, it's suppose I hand you a sequence of length n, L1, L2 up to Ln, where the LKs come from this alphabet of size 3, A, S, or N. And A signifies that all, in the kth position, A signifies that all principal minors are non-zero. That's all I'm telling you. If I put an S in the kth position, then I'm saying some of the minors are non-zero and some of the minors are 0, right? That you're somewhere in between. And if I put an N in the kth position, I require that all of the K by K principal minors, I require none of the K by K principal minors to be non-zero. So I'm not telling you all the values of those minors. I'm simply telling you whether they're all non-zero, some are non-zero, or none are non-zero. And then the question becomes, if you hand me a sequence, can I find a matrix A that has that particular sequence? That's also an unresolved problem, but we can say lots of interesting facts. And so here's some of these facts. And what we've gotten into is sort of looking at pattern avoidance or forbidden submatrices. So as long as you avoid the field of characteristic 2, then these words of length 3 are not allowed to occur as a subsequence in contiguous form in the enhanced principal rank sequence of any symmetric matrix. So you're not allowed to see these two subwords in there. So if you're gonna, if you're gonna solve this problem here in this sequence, you're not allowed to put NaN anywhere in that sequence, or NaS and so forth. And in fact, we worked out all of the forbidden 3x3 words here that aren't allowed. That doesn't characterize the sequence that I just talked about, but it gives you some hint, right? So, as mathematicians, now we need to worry about 4-letter words and 5-letter words and so forth, if that was something we were interested in doing. And indeed, we've done some work along those lines, but I just wanted to highlight that there. Now, moving further, so we've talked about principal minors and this principal minor assignment problem, and sort of expanding it by simplifying the conditions to this notion of EPR sequence. So I began to work with a grad student who was hoping to become a postdoc of mine, and he proposed the following. He said, look, what if we extend the notion of EPR sequence to something we refer to as QPR, which I'll define for you. Okay, so this is a bit of a mouthful, but I'll try to go through it with you folks slowly. So you have a submatrix. So now the matrix is designated B, and you have some submatrix B alpha beta. And the Q stands for quasi. So this submatrix is called quasi-principal. Excuse me. If, first of all, the matrix has to be square. So you require the number of rows to be the same as the number of rows to be the same as the number of columns. But I require this condition, that the intersection between alpha and beta has to be, well, obviously it's no more than the size of alpha by obvious subset relations, but it can't be any smaller than alpha minus 1. So what does this technically mean? Well, if if equality holds here, then I'm just back to good old principal submatrices. That means alpha has to be the same as beta, and that's something I've talked about previously. However, if equality holds here in this lower inequality, then what does this mean precisely? This means that the index sets alpha and beta differ in exactly one index. Okay? And if you have a submatrix that's square and the row and column set differ in exactly one position, that's called an almost principal submatrix. And so that relates back to the title of my talk, the almost principal submatrices. So what we're going to study is we're going to study these matrices. So both principal and so-called almost principal. And what we did is we mimicked the previous thing. We're going to talk about this characteristic sequence. This characteristic sequence is a sequence of length n. It has 3 letters ASN, depending on whether all, some, or none of the quasi-principal minors are non-zero. So it's the same idea as before, except you're expanding your list of submatrices. You're including this, what I want to claim is an important notion of almost principal. Okay. So the question becomes, can we get after characterizing this sequence? And I want to remind you, and I know I went through this quickly, but we don't know how to characterize whether a given sequence of AS and Ns is an EPR sequence of a general matrix A. We don't have a resolution for that problem. I mean, we're searching for it. We don't have a general resolution. So the idea is, as mathematicians, you understand, look, how about I expand the constraint list? Expand the constraint list, sometimes that introduces more structure, and then maybe you can get after a characterization. And indeed, we were lucky enough to find a characterization when we expanded our list to include quasi-principal submatrices. And that's the theorem here. So you hand me a sequence of length n consisting of the letters ASN in some fashion. Then that sequence is attainable. That is, it is the QPR sequence of some symmetric matrix as long as the field has characteristic 0. We had some little constraint here that we had to deal with. We can probably get rid of that as long as the field, if it had finite characteristic, if it had non-zero characteristic, the field would have to be infinite. But nonetheless, let's just leave it at this stage. This sequence is realizable as the QPR sequence of a symmetric matrix if and only if the last digit can't be an S. So right here, you cannot have an S in this last position. One of the reasons is because the last position only has one minor, namely the determinant. So you can't have an S in the last position. I would consider that an obvious condition. And then here's the other one, is that you can't see this subsequence of length 2 nor this subsequence of length 2. So as long as you avoid those two subsequences of length 2 and this obvious necessary condition, you can find a symmetric matrix with that QPR sequence. So we were really excited to sort of realize an actual, sort of formal characterization, albeit over the fields with characteristic 0, but it finally sort of did give us a broad feeling. And as I said, if you restrict the characteristic to be non-zero, this theorem is not true in general. And so if the finite field with characteristic 2, you end up with problems. But I think if the field is still infinite, this will hold. But nonetheless, it allows for more interesting research. But we were really excited to realize that we finally had a general characterization over these fields of characteristic 0. So then we asked ourselves, look, did this characterization result actually come from the fact of considering almost principal submatrices? And if so, what if I dropped the reliance on principal and only considered almost principal? Will I still get a theorem? And that led us to the notion of APR. So APR, this is what I just asked ourselves, should we just worry about the presence of almost principal minors? So the A in APR means almost. And again, it's the same, you play this same game as mathematicians. We're creatures of habit, and we just go through this idea to see how far we can push this. So I define what's called the almost principal rank characteristic sequence, the same game as before. You have 3 letters, ASN, and you want to see if such a sequence is realizable. Now, let me point you out to one difference. Notice this sequence only goes to length n minus 1. That's because there are no n by n almost principal submatrices of an n by n matrix. The only n by n submatrix of an n by n matrix is the whole matrix itself, and that's not almost principal. So you have to kind of stop at size n minus 1. So that's one little difference in this game. But it's a natural question to ask. Well, okay, I think it's a natural question to ask. I mean, some might argue that it may not be interesting, but I think it is. So because almost principal minors may not be understood by lots of people, I'll give you an example. I avoided examples in the previous settings for lack of time. So here's a symmetric matrix, very simple. And I claim if you look at all the almost principal minors, this is the sequence that pops out. So let's just go through this together just so we understand. In the first position, the 1 by 1 almost principal minors are exactly the entries off the main diagonal. You're not allowed to sit on the diagonal. So here, this 1 by 1 almost principal minor is non-zero, but this one is 0. And so that's why I put an S there, because some are non-zero and some are 0. Now, I'm not going to waste your time going through all the 2 by 2 almost principal ones. You folks have better things to do with your time, but you can check that if you take here's a 2 by 2 almost principal submatrix, you can check its determinant is 0. And in fact, they're all 0. And that's why I put an N in that spot. And then in the 3 by 3 case, you just have to do a little bit of work to check that some are non-zero and some are 0. But trust me, you can check that. And when you're bored, you can have fun with that. So we started constructing properties. And here's something I mentioned. If the first position here is an N, that means none of the off-diagonal entries are non-zero, which means your matrix is diagonal. Okay, that's interesting. If in the sequence of a potential APR sequence you see a double N, you see N, then you must have N's ever after. Okay? So once you locate 2 N's in a row, 2 consecutive N's, then you must have N's for that point ever after. And it turns out that the 2-letter word NA cannot occur as a subsequence, which is reminiscent of what happened in the QPR situation from before. And not to waste any more of your time, here is a theorem we came up with. It's not a complete characterization, sadly, because you'll notice that I've reduced the alphabet. I took away the letter A. It turns out that insisting on the letter A does lead to some very interesting constraints that we haven't been able to quite understand. But if you drop the letter A from consideration, we can characterize the possible APR sequences. And just as a matter of notation, this N with a bar over it just means N could be repeated, or it may not exist, just depending how you want. So it's similar to arithmetic. When you put a bar over top, that pattern repeats. That's what I mean there. So that's a partial characterization, I suppose. But please notice I've dropped the letter A from consideration. If you insist on putting the letter A in there, then we only really have a necessary condition. And you'll notice that there's this weird sequence that's allowed. And once you scrap that sequence, then these 2 subwords are not allowed. It's very curious what's happening. Here you see NS sits there, but that's the only sequence that can have NS. Very curious. And then if you're not this guy, then you're not allowed to have NS at all. It's strange. So this condition or this condition, not an and. And now let me just go to one last topic. I think I'm close to having time come up, but I do want to talk about this other notion of rank. So I began my talk by saying the rank was the size of the largest invertible submatrix, and I said for symmetric matrices that rank can be reinterpreted as the size of the largest invertible principal submatrix. So then myself and my colleague that worked on this problem said, wait a second, what if we actually defined a new notion of rank based on the size of the largest invertible almost principal submatrix? Because that would help us understand these sequences that I just mentioned a few slides ago. And, because we're not particularly good with names, we just called this the almost principal rank. So you look at all the almost principal submatrices, you take all the determinants, and you find the size of the largest invertible almost principal submatrix. So if I go back to my example that I showed you a moment ago, there is a 3 by 3 almost principal submatrix here that's invertible. And so the AP rank of this matrix is 3. And it turns out 3 is the largest it could possibly be for this 4x4 case, because the AP rank can never exceed n minus 1. And because the rank of a matrix checks all submatrices, of course, the AP rank cannot be any larger than the conventional rank. Okay, so there's an example that sort of highlights this. And so we began to study, what could the AP rank be? And we had an idea of what was happening here. We just had to work hard to prove it. And so let me just present to you some facts, and I'll present a simple proof because I do like to include one proof, but it's very basic because I don't want to waste your time. So the AP rank of a matrix is 0 if and only if the matrix is diagonal. That's something to understand. I mean, generally when we think about rank of a matrix, if the rank of a matrix is 0, then you've got the 0 matrix in your hand, but not for the AP rank, because the AP rank in some regard ignores the diagonal. But if you have a matrix that's, okay, symmetric is the overarching. Now I don't want to be diagonal anymore because I understand diagonal matrices. So suppose I'm non-diagonal, and suppose it happens to be invertible. So I hand you an invertible non-diagonal matrix. What is the possible AP rank? And this wasn't a surprise to us. The AP rank can't be too small. In fact, if the rank of B is n, then the AP rank has to be n minus 1. And this isn't a surprise. And I suppose if folks thought about it for a little while, you would see that this is, and here's one proof that we came up with. The matrix is invertible, so consider the inverse. Now, because I've assumed the original matrix was not diagonal, it turns out the inverse cannot be diagonal. Because if the inverse of a matrix is diagonal, then the original matrix must have been diagonal because BB inverse is the identity, and the identity is a diagonal matrix. So if I start non-diagonal, the inverse is non-diagonal. But everybody knows that the entries in the inverse can be calculated using the adjugate matrix divided by the determinant, and the entries in the adjugate matrix off the main diagonal are almost principal minors. You can check that. And so this is a simple little proof that if the rank of B is n, then the AP rank is n minus 1. So then the natural connection is, look, is the AP rank always 1 less than the rank? Right? So here the rank is n, here the AP rank is n minus 1. And so we were led to this question, and in fact we say, first of all, the answer to that question is no. The AP rank can equal the rank, and this is a situation where it can, but it is not too far off. So please don't fret about all the notation here. Simply just concentrate on this inequality. As long as you have a matrix that's not diagonal, I mean, the diagonal guys are kind of the 0 matrices in this world. So suppose you have a non-diagonal matrix. That means it's interesting. Then the AP rank is always between the rank and the rank minus 1. And then the question is, how do you characterize when it's one or the other? That depends on this parameter t that I just mentioned here. But I don't want you to fret too much about it. I just wanted you to be aware of this inequality. And I don't think this is actually a surprise to many people because the almost principal submatrices are so closely related to the principal submatrices. But nonetheless, we get the result that we desire. And so we were very happy about that. Okay, in the last minute here closing, I have just a couple of comments to say. So the work on the almost principal part and the quasi-principal part was work with this gentleman, Xavier Martinez Rivera. So I appreciate his kind help and work. And of course, the opportunity to speak at this meeting is wonderful. I certainly appreciate it. And I need to thank everyone for their help in assisting me in arranging this presentation. Prasad and Umash Shakara. I know I didn't say that very well. I apologize, but I appreciate all your time and help. Here are some of the references, and I'm happy to take questions if you have any. Thank you very much for your time.
Thank you, Sean. We have just a brief amount of time. Are there questions for Sean? I have a question.
It's a question. Not today.
Okay.
Can I make a comment?
Please.
Somebody is trying to come in. notion of, I think it is by Fiedler, of the off-diagonal rank. That means you look at all submatrices which do not intersect the diagonal and take the maximum rank. I think it is called the off-diagonal rank. And there are some very interesting results about inverse of a tridiagonal matrix and how the off-diagonal rank features. So this is more of a remark that have you looked at the notion of off-diagonal rank, and maybe it will suggest some problems. So just a remark. Otherwise, it was
Thank you for the question. I haven't considered formally the off-diagonal rank. I know what you're meaning concerning the inverse of tridiagonals. Those are called, I believe they're called like Green's matrices. And so there's this idea that somehow off the diagonal in a tridiagonal case, the ranks are 1, I believe. You know, they have this very special property. But no, I mean, we basically started at principle and we just started to move away from the diagonal in a different sense, where you compared the intersections of rows and columns. But it's a worthwhile, you know, property, idea for sure. But I have not formally considered it in terms of these sequences or inverse problems. Thank you.
Thanks very much. Let's thank Sean virtually one more time. And we'll move on to the next speaker. So it's a pleasure for me to introduce T. Krishna Kumar, who's from Rockville Analytics in the United States. And he'll speak to us about probabilistic foundation of econometrics. This is Dr. C.R. Rao's contributions. Please.
I thank Professor Manjunath Prasad and Mahe for inviting me to make a presentation here in this conference in honor of Professor C.R. Rao, in honor of his birth centenary celebration. And I would like to take this opportunity to invite all of you to a Facebook page that I have created called Dr. C.R. Rao Birth Centenary Celebration. I like you to use that platform to share anything you have to say about Dr. Rao and his contribution, including any pictures, videos, or anything. That is a depository of all those things that many people have already shared, and that I am planning to use that to bring out a publication on the occasion of his birth centenary. I'm going to talk today about Professor C.R. Rao's contributions to the foundations of economic science, which means econometrics. It's a quantitative analysis of economics that has mathematics and statistics applied to economics. This interest of mine in Professor Rao's work actually should have started in 1961-62, but unfortunately, I picked up his work only in 2010 when we were organizing his 90th birth conference at C.R. Rao Institute in Hyderabad. The story is like this. In 1961, when I was working at ISI Calcutta as a research scholar, Dr. Rao confronted me and said, "Why are you still here? We would expect you to go to USA to do a PhD in econometrics." I said, I need a letter of reference from 2 econometricians. I got only one. I need one more. He said he would give one. I said, "Dr. Rao, you are a very well-known statistician, but you are not an econometrician." Then he asked me to go to the library and see 1947 issue of Econometrica, which I saw. And then I saw an article by him, which is called A Note on a Problem of Ragnar Frisch, published by Frisch himself as the editor of Econometrica, on the basis of a recommendation from Harold Hoteling, forwarding Dr. Rao's paper. And the paper dealt with a very simple problem posed by Professor Frisch to Neyman in 1936 European meeting of the Econometric Society meetings. And the problem posed was simply like this. Suppose there is one regression, x1 regressed on a variable psi with an equational error alpha, and there is another regression, x2 regressed on psi with a regression error beta, where psi, alpha, and beta are random variables. Under what distributional conditions of psi, alpha, and beta does x1 have a linear regression on x2? And this problem was actually solved by Dr. Rao in 1943 as a part of his MA thesis in statistics at Calcutta University. And he communicated it to Econometrica through Harold Hoteling in 1947, when he was at Cambridge, still working on his PhD with Sir Ronald Fisher. And the theorem he provided in that paper is the starting point of a series of papers he and his students and colleagues had written over the years on characterization problems. Some of you must have heard his work with the Russian mathematicians, Linnik and Abraham Kagan. So there is a book, Linnik, Kagan, and Rao, on characterization. All that work and the work done by his students, Laha, Khatri, and Ramachandran, all those things, and Shanbag, all of them dealt with characterization problems. And another of his students, Professor Prakash Rao, has also written many papers on characterization, and he wrote a book on characterization issues. In fact, Professor Prakash Rao and I are picking up what I am talking about today to work a little bit more on Dr. Rao's contributions. So the problem solution was answered like this. Random variables psi, alpha, and beta have finite means assumed. Assume that without loss of generality, those means are equal to 0. Assume that beta is independent of psi and alpha, and expected value of I given psi is equal to 0. Then a necessary and sufficient condition for the regression of x1 on x2 to be linear for all A and B is that the characteristic function phi t of psi and the characteristic function omega t of beta are of the form given in the slide. E to the power minus c absolute value of t raised to the power d, and the other one is c prime, more or less similar, for some positive constant c and c prime, and a d that lies between 1 and 2. That theorem, looking at those numbers, doesn't mean much, but a careful analysis will show that those characteristic functions refer to a very wide class of distributions called the distributions that follow a stable law. Stable law is the one where if two random variables have a distribution, their sum also has the same distribution. And in this family of stable law distributions includes symmetric distributions with finite means such as normal, and includes symmetric distributions even with infinite moments such as Cauchy, and it includes asymmetric distributions with fat tails such as Levy distributions, which are very common in economics. So, although this particular problem has been posed by Frisch and answered by C.R. Rao And although C.R. Rao and his students and colleagues worked further on characterization problems, starting from this basic problem, it so happens that none of these people have actually examined how the particular question arose. What is the basis for Frisch to raise this particular problem? Now, Frisch is the founder of econometrics. There was no econometrics before. Frisch started the Econometric Society in 1930 and started his journal, for which he is the founding editor, in 1933. And before econometrics developed, he laid the foundation and he said, application of statistics to economics requires building econometric models where you explain some economic variables, how they depend on each other through a set of equations, and then assuming that the economic observations are observed, there are observational errors, and then you write, there is a matrix vector equation I wrote on the slide, AX plus B psi is equal to 0. That is a deterministic equation in matrix notation, where A is a matrix n by n matrix and B is an n by m matrix, and X is a vector n dimensional, psi is a vector m dimensional. So that the set of equations show there are n equations in n unknowns, the X, involving some other variables called exogenous variables psi. Those are called structural equations in economics, and those actually form the econometric model. Then there's a normal procedure whereby you ask the question, given the exogenous variable psi, what are the values of the endogenous variables x? And that is answered by deducing from that equation what is called a reduced form equation through a matrix operation. X is equal to minus A inverse B psi or equal to gamma psi. That's called reduced form equation. So this is the problem. And from this problem, one can write down a regression equation. X is equal to gamma psi plus an eta, which is a vector of random variables, such that expected value of x given psi is equal to gamma psi. So then Frisch raised the question, what should be the distributions on psi and eta such that the left-hand side variables in that vector x, there is a linear equation. Okay. Now, if you take a special case of that, with only one exogenous variable psi and only two endogenous variables 2, x1 is equal to a psi plus alpha, x2 is equal to b psi plus beta, and psi, alpha, and beta are random variables. Under what distributional assumptions between psi and alpha and beta is there a linear regression of x1 and x2? So this is a highly special case of a more general problem of building linear structural econometric models. The interesting point to note is that at that time, there was no probabilistic basis for econometric models. How does probability enter into economics? Because we don't do random experiments, we don't do a sample service to get the data. You get the usually what is the officially recorded data. So where does probability enter? So Frisch's idea was that probability enters because we make observations and observations have errors. So these regression models are supposed to be regression models with variables observed, measured with error. What happened was in 1940s itself, even before Rao's paper appeared around 1944, the Econometric Society developed econometric models by omitting errors in variables and including only errors in equations. Hence, all of econometrics is developed with errors in equations and not errors in variables. And then people assume that errors in the variables or errors in equations have normal distributions. And then went ahead and applied maximum likelihood using a multinomial normal distribution for the errors. So the whole question of errors in the variables, what distributions those errors in variables will have, all that was assumed away or ignored altogether. As a result, people had no interest in the work that was done by Professor Rao. And there is a lot of interest in errors in variables models also. And there is a need to return to this problem. For example, if you take a slightly improved model compared to his 1947 theorem, namely x1 depends on not on one variable psi, but two exogenous variables psi1 and psi2. And similarly, x2 depends on two exogenous variables psi1 and psi2. So instead of one psi, I put 1 and 2, psi1 and psi2. Let me call that a 2 by 2 problem. Then, as an economist, I would like to ask, or Frisch would have asked, not only there is a regression of x1 on x2, but is there a regression of x2 on x1, which is independent of this? Can there be two independent regressions, one x1 on x2 and another x2 on x1? And a solution of those two regression equations would solve x1 and x2. And that is that first structural equation I wrote, ax plus b psi is equal to 0, is that equation. So the question is, from this problem, does there exist, or do there exist, more than one linear regressions between x variables? Is a question that an econometrician is interested to know, but unfortunately, by not relating the problem which Dr. Rao solved in 1947 with the basic reason why Frisch raised that question, all mathematicians and statisticians who worked on characterization problems have missed answering those questions. As a result, econometrics has not developed. Econometrics with errors in variables has not been developed. And the characterization people have not looked at very interesting problems that arise as a result of its applications to economics. So it is my feeling that there is an immense scope for further work in this area. In fact, for this problem, which I mentioned, when I take psi1 and psi2 as two variables, under what conditions there will be two equations, one regression x1 on x2 and another x2 on x1. That has been recently worked out at my suggestion by Professor Velas Prakash Rao. And he has come up with a result that two independent regression relations between x1 and x2 will occur under a necessary and sufficient condition that psi, alpha, and beta, all three of them are normally distributed. Okay. Again, perhaps that can be generalized by relaxing some other conditions. So that must be looked into, because it will be much more useful if such linear regressions can happen with psi, alpha, and beta having table laws, just as in Rao's 1947 theorem. Not only that, an econometrician would ask the question, not only if a linear regression x1 and x2 between x1 and x2 exists, he would also ask the question, under what distributional conditions such a linear regression which exists is estimable. That means its parameters can be estimated with precision. Again, Professor Rao has contributed a lot on estimation of linear functions of parameters in linear models. Rao's contribution is immense in that, and that is related to what we call in econometrics as identifiability. So Dr. Rao's contributions extend to laying foundations of linear econometric models, probabilistic foundations, and identifying those models, and also estimation because of his Rao-Blackwell theorem, as well as the maximum likelihood estimates and the second order efficiency of estimators, and all those things are immensely useful in the development of econometrics. So I would say Dr. Rao laid the foundations of all branches of econometrics. And his core method for calculating maximum likelihood estimates is widely used by econometric softwares. Any econometric software you take, that is there. And Rao's core test is widely used by econometricians. I think I have taken a lot of time. I thank the organizers for giving me this opportunity to make the presentation. Thank you.
Thanks very much to Professor Kumar for that interesting description of Professor Rao's foundational contributions to econometrics. Do we have questions or comments?
Any statisticians asking questions?
Any questions or comments for the speaker?
Yeah, thank you.
Please.
Most of the people are with YouTube who are not participating, interacting.
Okay, very good. Thank you. So let me thank both the speakers in this session, Sean Fallett and T. Krishna Kumar. Thank you very much.
Do you want to take a break? Thank you. Accept it. Want to take a break? We are continuing. Okay, we are continuing next session. Thank you.
Thank you, sir. Thank you, sir, for chairing the session. Without any delay, let us go with another session of Innovative Talks. We have with us Professor George P.H. Tan, Professor Anand Godbole, Professor Adi Ben Israel, and Professor S.K.J. George P.H. Tan is an emeritus professor at McGill University, Canada. His title of presentation is When Math Meets Art, with postage stamps and magic squares. Anand Godbole is a professor of mathematics and statistics, East Tennessee State University, Johnson City, USA. He will be talking on birthday and coupon collector problems with dependents. Adi Ben Israel is an emeritus professor at Management Science and Information Systems, Rutgers Business School, New Jersey. He is going to speak on matrix volume and its applications. Surender Kumar Jain is an emeritus professor at Ohio University, USA, who will speak on influence of Rao and Mitra in my research on generalized inverses. We are pleased to have Bhaskar Rao P.S. Koparty, Professor and Department Chair at Indiana University, Northwest USA. I request you to chair this session. Over to you, sir.
Thank you. I hope everybody can hear me. This is KPS Bhaskar Rao.
Yes.
I would first like to congratulate and compliment Prasad, Manjunath Prasad, and his team for organizing this online conference. Because of the COVID, we have to miss meeting in person. I am sure all of us have many memories of meeting in Manipal, and we hope that in 2021 we will meet in Manipal. May not be in 2020, is not in 2020 definitely, but hopefully we will have better days. And it's a great pleasure to chair this session. Oh, I would also like to mention that I would like to get some credit for this conference indirectly, because Manjunath Prasad did his PhD under my supervision, which I am very proud of it. And it's a fact which some of you may not know. I thought I will mention this to you. I'm honored to chair this session in which some luminaries as George Stein, Ben Israel, Anant Godbole, and Professor Jain are presenting. And it's a wonderful opportunity for me. And we will go with the first session now. I have heard George's talks a few times. I had the opportunity to hear him. He is an inspiring and exciting speaker. And I have read many of his works. And I also have read many of his students' works on matrices, of course. And I would like to invite George to start his presentation. Prasad, you will play the recorded session first, or whatever is the plan, please.
Okay, thank you. Yeah, please.
This is page TK1. When math meets art for Professor C.R. Rao, and Night Tours. Karlok Chu, who's with us, Simo Puntanen, who's in Finland, and George Stein, who is me, here sitting in my home before my computer at an Hans Island in Montreal, Canada, Quebec, Canada. These slides were prepared yesterday, December 9. Today is December 10, which is actually the 100th and quarter birthday of C.R. Rao on 10 September 2020, exactly 3 months ago today. And it's an invited booklet, invited talk. The first 27 pages we're going to do now, and the last 120 pages, the whole shebang, is for the e-souvenir booklet. So many happy returns, Professor C.R. Rao, of your 100th birthday, exactly 3 months ago, 10th of September 2020. We're indebted to you for your encouragement over these years of our research in matrices and statistics. In particular, George and Evelyn Stein, thank you again for your invitation to visit the Indian Statistical Institute Delhi Center in February and March of 1976, 44 years ago. Very special thanks go to Awani Kumar for his substantial help with Knight's tours. I consider him to be a world expert on Knight's tours, and I'm so delighted that he was able to help us. We also found most helpful an online report by Rob Gabler and Chu Wang Yang, dated August 1999, so 21 years ago. So as I know, that's not published, it's only online. More acknowledgements will appear on page TK38, but we're today only going to page 27. So we begin with the special philatelic cover, 2009 for Professor Rao. And then we're going to go to a full page number 1 of children's drawings for 100 stamps. In between, we're going to the postmark on the previous page. You see that postmark over there from the AIMSCS. You must know that pretty well. That's the C.R. Rao Advanced Institute of Mathematics, Statistics, and Computer Science, founded in 2007 as a leading institute for basic research in statistics, computer science, and mathematics, and it's located on the campus of the University of Hyderabad. Here is this beautiful philatelic sheetlet of Indian traditional arts for greetings, and it was used, the top left stamp was used in the special cover that we just saw. Here is the 10 by 10 sheetlet of 100 stamps. This is mathematically very interesting, as you'll see in a few moments. These were children's drawings to celebrate Christmas in 1970, exactly 50 years ago. These are Canadian stamps. At that time, the going rate was 5 cents. Now it's $1 or $2. So here's a smaller image of that same top left-hand corner of the previous page. Top left-hand corner is diagonal going from right to left. And you can see that it is a one-step backwards circular Latin square matrix, defined as in display 3. The coded matrix that we have in display 4 has this characteristic polynomial, showing that it is, in fact, doubly keyed. This extends some results that I published with Peter Lolly in 2010, so 10 years ago, and very recently with Karlok Chu and Simo Puntanen, we produced a report on illustrated comments on 5x5 fully magic squares and 5-fold symmetry. This was in 2014. So the golden ratio, which was listed in the previous overhead, 1 plus the square root of 5 all divided by 2, is illustrated in this beautiful sheetlet from Macau. The golden ratio being defined as the ratio of the sum of two quantities, the larger of the two quantities to their sum. That is written out, I guess, in various places in that sheetlet. We now have another sheetlet also from Macau, now in China, of a tortoise or turtle, and the back of it, which shows the Loshu magic square, 492,357,816. It's fully magic in every row and column, and in the two main diagonals add to the same magic sum m. It's classic when its n squared entries are the integers 1 up to n squared, and then m is a half n into n squared plus 1. When n is equal to 3, then m is equal to 15, and when n is equal to 4, then m is equal to 34. Here, with 492, you can see that the rows, columns, and diagonals all sum to 15. In early history, such squares were devised in India, as well as Arabia, China, Greece, and Japan, where they also served as charms against all kinds of ailments. One of these magic squares, known as the Loshu, is the one in the left-hand corner, the scroll of the river Lo, which is a tributary of the Yellow River, out of which came a tortoise or a turtle rising up from the water with this magic square on its back, approximately 4,000 years ago. This delighted the emperor, since he found the fully magic 3x3 matrix on the tortoise's back. Very recently, I got an email from Gert Strenkler, who's a close friend and collaborator on my research over many, many years now. And he posed this matrix D, 1/6, and then it's a very hairy 3x3 with square roots of 15 all over the place. And I'm happy to tell you that I was able to corroborate our guess, the matrix D being a cube root of the Loshu matrix. I think this is a new result. I don't think I've seen this anywhere established, and there is a short proof, which will hopefully appear in the e-souvenir booklet. We also study the Jisu-Gyu Mundo, or hexagonal tortoise problem. So this is a different tortoise to the one we just saw. The idea here being that these hexagons are such that you number the n equal to 30 vertices of a grid with h equal to 9 hexagons, in which the 6 vertex entries in each hexagon add to the same magic sum, m here being the central magic sum, defined to be 3 into n plus 1. N here is 30, plus 1 is 31, times 3 is 93. We adapted choice HTP to philatelic lattice grids with 4-sided stamps. In this example, the PLG is defined in the sheetlet as introduced above for the traditional arts. Somebody, I hope, will tell me a little bit more sometime about these traditional arts. They were issued by India Post Office in 2009, so just over 20 years ago, just over 10 years ago, with 4 stamps in a 2x2 grid. The top left-hand stamps, as we've already discussed, was now these philatelic lattice grids that we have adapted from choice HTP, the hexagonal tortoise problem, are discussed in a joint paper by Chu, Puntanen, and Stein in the farewell issue of the Journal of Mathematical Philately, which sadly ceased publication a few months ago. Here's the grid in the top left-hand corner that we define for this 2x2 philatelic grid. And the objective here is to find a number here, magic number m, equal to 16. We claim that that is the minimal number, as you can see by where I'm pointing the cursor. I hope you can see that. Okay, and let's continue. The Montreal Gazette is a joy to read every morning when I get up at 7 o'clock to pick it up outside my door where it has been delivered. And I'm really pleased that from time to time they publish a chessboard. Now, these chessboards yield Knight's Tours, which thanks to Awani Kumar, who maybe you know, he's in Lucknow. He works for the Forest Service in Lucknow, gave us this closed semi-magic Knight's Tour. It's closed because the numbers 1 and 60 are a chess knight apart. And he noted there is no magic tour on the 6x10 board, which is what this is, that this clown in Lima, Peru is holding on this suitcase. The 6x10 board, the smallest rectangular board on which a magic tour is possible, is 4x18 or 6x12. That is a 72-cell board. All column and row totals here are semi-primes. There are 183, which is 3 times 61. And the row totals are prime multiples of 5, either 295, 265, 305, and 335. Moving right along, TK16, we are over halfway. This is a very nice stamp showing a beautiful painting by the relatively famous artist Matisse. Henri-Émile Benoit Matisse was a French artist known for both his use of color and his fluid and original draftsmanship. Hawani Kuma gave us this interesting and apparently challenging to compose Knight's Tour. The first 8 perfect squares, 1 up to 64, are up there in red, and they are all in sequence, 1, 4, 9, 16, 25, and they are all equidistant from the center, 75. This is known as a figured Knight's Tour, which Awani Kuma tells me has aesthetic appeal. In the penultimate issue of Philomath, there was a column by William Sharp, who exhibited this stamp for Chu Chung Chi, an ancient Chinese mathematician, so over 2,000 years ago, who determined that the value of pi was somewhere between 3.1415926 and 3.1415927. In the Scott Catalog, it's 246, and it was issued in 1955. In the top right-hand corner, which I'll come back to, is an image of an artist colony house in a small town called Worpswede, near the relatively large town of Bremen in northern Germany. And it was issued for the centennial of this small artist colony. So it certainly satisfies the art part of the title of this talk. There's also a little side homework exercise to which I have not yet found a solution. Apparently, a to the b equal to b to the a will hold only for non-equal positive integers if a and b are 2 and 4. So when you guys who are watching this have nothing better to do, solve this homework exercise and send me an email. So here is an enlargement of this house front. It's called Sommerabend, which is the German for summer evening. It was painted in 1905 by Heinrich Vogeler, who lived from 1872 to 1942. And the house was called Bakenhof, Birch Tree Cottage. There is a dog in the front, which I first thought was a goat, but it's not. It's a goat. It's a dog. There's Heinrich Vogeler on this beautiful philatelic maxi card. And here are 2 copies of the same stamp again. He also did decorative drawings for the town hall of Bremen. He was a painter, designer, and architect. But let me tell you about Worpswede and the mathematical congress that was held in Bremen. The mathematicians asked for a stamp from the German Deutsche Bundespost, German post office, but they decided against it. But instead, they issued a stamp for the artist colony. The 2 meetings were 1 year apart, and as Professor Friedrich Hirzebruch from Bonn said, since mathematics is also art, we consider ourselves honored by the commemorative stamp, 100 years of the artist colony. We feel united in spirit with the artists of Worpswede and consider their stamp also as ours. I haven't yet been able to find Miscellanea Mathematica. Our McGill library is closed because of COVID-19, but when I do, I look forward to reading a report on that Bremen Congress. But I do concur with Professor Hirzebruch that there are close connections in the way of working and thinking between mathematicians and artists. This Michael tour was an act of friendship and solidarity which appeals very much to me. So here are some different kind of stamps, but they're still mathematically connected. And the design is again by our friend Heinrich Vogeler. These are newspaper advertising stamps, and they are advertising the Hanover cookie factory Balsen, which is best known for its Leibniz cakes. And cakes in German is the same as cakes in English, only a different spelling. It was introduced in 1891. At that time, brand name marketing was in its infancy, and Germany decided through its first Balsen CEO, Hermann Balsen, he chose the famous philosopher and mathematician Wilhelm Leibniz. Here are two very recent stamps, 2018 and 2019 from Ukraine of Leibniz. The TET in these stamps, I have since discovered, refers to a very durable wrapper that these cakes, cookies, etc., were wrapped up in. And I also understand that these are drawings from a German fairy tale, children's tale called Hansel and Gretel. So Hansel and Gretel, also in English. In the Faroe Islands, of which I always have wished to visit but have never visited, here is a stamp that they dedicate to Fyrtal. Fyrtal apparently is the Faroese, that's the language spoken in the Faroe Islands, for four-handed chess. So this is a chess board, which is the usual 8x8 board, with 3x8 extensions on the four corners, which makes a grand total of 160 squares. Each player's 16 pieces are placed appropriately on these outermost rows. There are four players, two players facing each other, and they must not give each other advice. The player is checkmated, the partner can help free him. If this fails, and the partner himself is checkmated, the pair has lost. Fyrtal, I guess that fear means in Faroese the English four, or the German vier, V-I-E-R, and T-A-L-V means chess. So this is vier Schach in German, usually played without time control, so games could become complicated and lengthy. Stories are told that games have been postponed in early summer in the Faroe Islands and resumed in the fall when the men returned from their summer fishing trips. Today, only a few in the Faroe Islands play this variation. The stamp shows the chessboard, not a cheese board, it's a chessboard, used for Fyrtal with four homemade chess pieces. From right to left, first of all, the knight, then the queen, then the king, and then the bishop. This is the only stamp that I think even exists, certainly the only stamp I have found for four-handed chess. Now, four-handed chess was written up in England in 1881, but it seems that it was known in India 300 and some years earlier in the Titi Tattva of Raghunandana Bhattacharya, 1520, so exactly 500 years ago, if I do the right arithmetic, to 1570. Anybody has access to this Titi Tattva and can find the details, I would be very interested. Here is the lead page from the internet of four-handed chess by Captain George Hope Verney. I was very happy to hear about him, that he was from Isha, Surrey, because I grew up from my pre-teenage years and teenage years in a town called Purley, very close to Isha in Surrey, England, just south of London. Here's a diagram of the extended chessboard for four-handed chess. Here comes the details about Raghu Nandana, who I understand was a Sanskrit scholar who authored 28 Smriti Digests on Hindu civil law and rituals, collectively known as Astavimsata Tattva, and the Smriti Digest is number 22. So if you can find all 28 of these, then the one to find is 22. In our Beamer file of 2010, so 10 years ago, we discussed an early method of making magic squares of order 4, having any optional magic sum to be given in this Smriti Tattva. And here is that magic square with a parameter A, and it doesn't matter what A is, you get a magic sum of 2A, and you get a magic key of 2A minus 17 multiplied by 8. That magic key is the negative of this guy, square rooted. If I got it right. In any event, it looks like I did. That's kappa squared. It's most perfect pan-diagonal. All the diagonals, as you can see, are also adding to 2A. Here we have the Knight's Tour, again, constructed for us by Awani Kumar. I don't know if this was very difficult for him to do, but it really is quite beautiful. And here is the stamp with that same chessboard on it from the Faroe Islands. And there's his square. It is not closed. 1 and 160 are not a nice move apart. Very recently, I don't yet have a Knight's Tour for this, that's still pending, is the Russian four-handed chess, also known as Russian fortress chess, which was certainly played in London in 1855, which is where was apparently played in London by Chigorin and Capablanca, a Cuban chess grandmaster, very famous. Capablanca, there's a picture of him down there in that stamp. Here's a stamp issued by Russia for Chigorin. He's much less famous. He only has one stamp. There are literally hundreds of stamps for Capablanca. Here you have a 4x4 fortress, and in each of those is a single gate to enter the chessboard in the middle with 2 rows, 2 columns on either side. And that's the last overhead, ladies and gentlemen. I thank you for listening. I thank you for making this Teams event. I hope that you've been able to hear me. Otherwise, I can give you a repeat performance at your convenience. It's a 120-page contribution that I sent you the other day. That was sent to Uma Shankaran Narari. At first 27 pages is this talk, and the latter part beginning with further discussion on choice, HTP, and the Greetings Traditional Arts sheetlet follows. And then follows also Margaret Kepner's Magic Square study. And we end that contribution for the e-souvenir with this 4x4 beautiful chemical magic square proposed by Jeffrey Bucock in his article Where Chemistry Meets Maths Meets Art, published in Voice, the quarterly magazine of the Royal Society of Chemistry, which was sent to me by Dennis John Bowden, who just very recently died at the age of 94. Okay, ladies and gentlemen, that is it.
Thank you, Professor Stein. It's an exciting talk, as always. And there's so much information in your talk that most of us have no idea at all. Only a little bit of it is known to us, and it is fantastic. I have a question before I open for others. Are there magic cubes too? Is Professor Stein here? Yes, of course, he's here. Yes. Are there magic cubes also? You have to unmute, I believe. Are you able to unmute?
Professor John Stein, we request.
Can you hear me now?
Yes.
Yes, sir. Yeah.
Yes.
Okay. Yes, there are magic cubes, and there are also magic night tours on magic cubes that have been created by Awani Kumar. In fact, he has just published two very recent papers, one which is hot off the press. I got a copy yesterday only, which goes into such information. I can, if you give me your email address, or maybe it's available here, I'll be happy to give you the references.
That would
Wani
be
Kumar
fantastic.
is the key man.
Yes, that would be fantastic. Okay. Any questions from anyone?
Indian
Can I
Foreign Service. He's a
Can I make a comment, George? Lovely talk. Do you know that there were issues of stamps in New Zealand in 1893 that had advertisements on the rear?
No. Maybe you could send me an email, Jeff. Nice to see your face. I see you at the bottom of my screen. You took off your glasses. Makes you look so much younger.
Well, I've had cataract operations now, so I can see a little better. Look, I can scan the pages from the Campbell Patterson catalogue that has about 4 panes of different layouts of the advertisements. I'll send you the details.
Thank you very much. I look forward to receiving that. You certainly have my email address.
Yes, I do.
George,
yes.
Is there a stamp related to Fibonacci numbers? It came up when I was teaching in my class, and I mentioned your name and your interest in this and your work. And one of the students asked if there are stamps related to Fibonacci numbers and golden ratio.
Yes, there are, including a stamp from Liechtenstein that actually has a mathematical error in it. There is a website run by a man called Jeff Miller on images of mathematicians. And again, if you send me an email with that, I'll be happy to give you the technical information.
Yes, fantastic.
There are many, but well, there are not as many for Fibonacci as you would expect. That is, there are not as many as there are for Newton and for Leibniz, but Ukraine has recently issued a large set of stamps for mathematicians, including, I think it is 2 stamps for Fibonacci, and I'll be happy to send images of these to you for your friend.
Thank you. Thank you. Okay, so we thank Professor Stein for the wonderful work, wonderful presentation to us. And So we move on to the next one. Prasad, we can do that.
You unmute now.
Now I
Okay.
have to mute.
All right. Our next talk is by Professor Anant Godbole. And I should mention that we were colleagues many years ago in 1986, I believe. 85, 86, I think. It was in Michigan Technological University. And of course, Anant was also from ISI, as many of us know. And I invite Anant to present his talk on birthday and coupon collector problems with dependents. Anant. You have to unmute probably. Yes.
Good morning, everyone. Thank you for coming to my talk. I will be sharing my screen shortly, but I just wanted to thank the organizers, particularly Professor Karantha and Bapat, and also Nupur Nandini for all her help. And I will share my screen now, and we will get started. Okay, the topic of my talk today is the birthday and coupon collector problems, but not the regular ones. The ones I will review the theory of those, but I'll be looking at the situation where you've got a lot of dependence. And the topic that I've chosen to talk about is covering and packing designs. So let me reminisce a little bit about something that came to my mind quite vividly. About 43 years ago, I was an MStat student at ISI Delhi. And Professor C.R. Rao had a seminar, or maybe it was a joint seminar, but he would assign papers in which that we had to present, read and understand and present. And one of the papers was on the Kramer-Rao inequality. And it was written by, it was a preprint actually, and I think it has changed since that time. Anyhow, it was written by my professors Fabian and Hannon, my later to be professors, when I would go soon after that to Michigan State University for my PhD. And I got together with a PhD student, Varadaraj Perumal, who was a student of Professor KRP. And we concluded together that the contributions in the paper were not quite as significant as claimed. And it was really a happy moment for me, but I got, got the paper a few weeks ago and tried to reconstruct what it is that we had done. And I'm sorry to report that I could not reconstruct what had been done. But let me toggle to the paper itself. It appeared soon afterwards in the Annals of Statistics, Volume 5, 1977. And the claim here is that there are sufficient conditions which are weaker than the traditional ones. And what Peru and I came up with was an argument that they were in fact equivalent. But as I said, I've been away from statistics for at least 30 years, and it was not an easy thing for me to do. Okay, so what will I be talking about today? First of all, I'll introduce the classical birthday and coupon collector problems, which I will rephrase in the format of packing and covering. And then we'll see to what extent the results and not just the results, but the nature of the results and the log factors, all that show up again when you look at covering designs. So, birthday problem. Suppose we're trying to pack balls in boxes at random so that each box contains at most one ball. Okay, and the point is that this is the so-called birthday problem because the moment you get a box with two balls, so the boxes are the 365 days of the year, the balls are the people's birthdays, they go into the appropriate box, and we're trying to, well, let's recollect that when capital N is 365, and small n is 23, then that is the time at which the probability of having a birthday coincidence goes over 0.5 for the first time. However, in this talk, I'll be interested more in thresholds, probabilities that go to 0 or 1. And one of the things in Barber and Holst, 1989, and it's been known before that, actually, it's in Feller volume 1. A lot of this is in Feller volume 1. If we throw little n balls into capital N boxes, the property holds with high or low probability at the threshold n equal to the square root of n. In other words, if little n is significantly smaller than the square root of n, smaller by an order of magnitude, this implies that there's the chance that there is a box with 2 or more balls tends to 0. On the other hand, when little n goes substantially larger than the square root of n, then the asymptotic probability of a coincidence is 1. And if you look at the square root of 365, it is about 23. So you're looking at the threshold when that happens. There's a generalization of this to at most G number of balls. It's again classical, but we re-derived it in this paper. This paper, by the way, is joint with 3 students, Thomas Grubb, Q.T. Han, and Bill Kay. And we used Talleyrand's inequality to do it. So here's the result. So when little n balls are randomly and uniformly distributed in capital N boxes, then if you define a random variable x being the number of boxes with G plus 1 or more balls, so when G is equal to 1, you get 2 or more balls, then if n is substantially smaller than or larger than capital N to the G over G plus 1, that tells you the probability that x is equal to 0 goes either to 1 or to 0. I've written this a little bit differently from the birthday problem. So when n is small, the chances that there are no boxes with a large number of balls goes to 1, which is what, it's an inverse way of saying what I did on the previous slide. So yeah, and when G is equal to 1, you get the square root of n. If you're looking for the threshold for 3 or more balls in a box, then that's n to the 2/3 and so on. But notice that the thresholds up here get closer to n equal to capital N as G goes to infinity, because the exponent approaches 1. However, it might still be the case that if you have n larger than capital N, it might be that not all the boxes will have a ball in it. So this is now leading to the coupon collector problem. So in terms of birthdays, how many people do you think you need to have before, at random, if each box is to have at least 1 ball in it? So that's the coupon collector problem, and it's again classical. You will find in Feller Volume 1 that the expected waiting time for each of the boxes to be filled is kind of interesting. It's n times log n, that's the leading term. Then n times Euler's constant is the second order term. And then you have n times something going to 0. So that's the error, I guess. And so that's roughly n times log of n is the waiting time. And the variance is roughly n squared. And there's constants, I think it's 6 over pi squared. So we've looked at each box containing at most 1 ball, at most G number of balls. Then you've looked at least 1 ball. This is coupon collection. So the question is, what about at least G number of balls? This is the result I'd like to focus on because it's the most nuanced of the lot. So this is a theorem that was proved by Lars Holst, and it generalizes previous work, but it's very definitive in its content. So it says that if you look at the waiting time until each box has at least G number of balls in it, then the expected value is your n times log of n, right? There's the Euler's constant. There's little o of 1. But this term over here, G minus 1 log n, is the most intriguing of the lot. It tells you that successive coverings of all the boxes are linear, but not in log n, but in log n. So this is the part that tells you that subsequent covers take lesser time and in the same kind of way. Then if you normalize this by dividing V of G by N, and then bringing those other terms over to the left-hand side, what you get is the distribution is extreme valued here of the, yeah. And if you, this talk is focused on thresholds, so you can easily take the previous result and make it into a threshold result. If X is the waiting time till each box has at least lambda number of balls, then the probability that X is less than or equal to so much goes to 1. But what is that so much? It's n log n plus lambda minus 1 log n plus anything that goes to infinity. Okay, so the chance that you get what you need in so much goes to 1, and it's the a sub n that dictates the fact that it goes to 1. Likewise, the chance that X is less than n log n plus n times lambda minus 1 times log n minus bn, that's a smaller number. The chance that you have X being less than or equal to that approaches 0 as n goes to infinity. Okay. All right, so let me switch to combinatorial designs. And over here, what we're trying to do is slightly different. So let's talk of a set of size n, that's your base set. And your job is to look at every set of size t, right? That's, you can think of those as your boxes. And what you're doing is selecting as few sets of size k so that every t set is contained in at least one k set that is picked. Of course, k has to be greater than or equal to n. There's an easy lower bound, n choose t divided by k choose t, which you can get by a simple counting argument. And what this combinatorially simplifies to is actually n choose k over n minus t choose k minus t. And this formulation is in some sense better because it gives you the fraction of all the k sets that you need to pick in order to cover every set of size t. And cover is in the set of set inclusion. So you need at least that many. And what the Erdős-Hanani conjecture is that this number is actually asymptotically correct if k and t are held fixed and you allow n to go to infinity. So yeah, and this was proved first by Rodel. But what if n is not going to infinity? If you just have n, k, and t, then you have this kind of an upper bound that Erdős and Spencer proved. N choose t over k choose t times 1 plus log of k choose t. Notice that this is also can be written as n choose k over n minus t choose k minus t. Then a couple of students and I got together about 25 years ago and found a result that said that actually if you want the smallest number of k sets so that each t set is contained in at least g of them, then interesting things happen. You get your n choose t over k choose t. Here's your log k choose t. But what you actually get is subsequent coverings need just log of k choose t. Same thing, the same kind of phenomenon. And so that is very interesting. But these results here and on the previous slide are looking at the minimum number of sets that you need. It's not looking at random behavior. So let's get into that. Let's start with the birthday problem. Now, so what you have is a C is a collection of sets of size k, in which each set of size k, each element of n choose k, is selected for membership with probability p. And what you're interested in is the number, you're interested in every t set being contained in at most lambda numbers of k sets. So we're looking at the at most problem, just like the birthday problem. So x equal to x lambda is the number of elements which are subsets of at least lambda plus 1 members of C. And then if P is small, that tells you that you have a small number of K sets, then the chance that there's no such set goes to 1. And if P crosses that threshold, the probability approaches 0. Thing to keep in mind is that if lambda goes to infinity, this part of the exponent approaches 0, and you're looking at a threshold at 1 over n to the k minus t, which is, if t and k are constant, then what you're looking at is something which is roughly the same fraction of sets that you had in the lower bound. Okay, so that was the packing result. And then for the covering result, what Svante Janssen and I got together and proved is that the cardinality threshold for single coverage is so much. So if you have n choose t over k choose t, which is n choose k over, here we go, it's n choose k over n minus t, k minus t, times log of n choose t. So the threshold number is a little bit larger than k choose t, plus or minus omega 1. Omega 1 is any function going to infinity. So if you have a large number, this much plus omega 1, then the chance that you've covered all the sets is it's a covering design with high probability, right? In other words, all the T sets are covered by a K set. And when you have minus omega 1, then the probability of that happening is low. It goes to 0 asymptotically. You might ask, what happens if you have log of n choose t plus some constant? And that too is in that paper. It shows that there's the number of uncovered T sets has a Poisson distribution with an appropriate mean. Now, in this work that I wanted to talk about, this is work that has been submitted to the Journal of Combinatorics. It's still under review. And in that, there's this covering and packing designs. There's also a section on CDON sets from additive number theory, union-free families, which is random subset theory. Anyhow, the point here is that let's take a look at this. What you get is that the threshold is, as announced before, for 1 coverage. You're interested in each T set being covered by at least K sets. So you have the previous number, you have the omega 1s, but then subsequent coverings take G minus 1 times choose T. And this is the part that I wanted to draw your attention to. I'm looking at the clock. I'll try and summarize the proof rather than try and go over it in any detail. You have a sum of indicator variables, x, and you want to approximate the distribution of x with the Poisson distribution. And the Stein-Chen method of Poisson approximation relies on the existence of a coupling sequence which models the distribution of the indicators conditional on the jth one being equal to 1. And if such a coupling exists, which is monotone in the sense that those j's are larger than i's, then the total variation distance can be expressed in just in terms of the mean and variance. Well, for the Poisson distribution, the mean is equal to the variance. So if a distribution is close to Poisson, you'd expect that this difference would be small. And then you'd have the distance going to 0. That's the rough idea. On this page, I'm describing the coupling. If I sub j is equal to 1, in other words, if the jth set is covered lambda minus 1 times or less, then you don't need to define j's any differently. On the other hand, if you have overcoverage, you're going to remove a certain number of k sets according to the appropriate distribution so that you get a sample outcome corresponding to I sub j equal to 1. And the D selection tells you that you must have j greater than I. Simplify the Stein-Chen bound, you get something like this. It really amounts to covariance calculation, the probability that both the first set and the jth set are covered lambda minus 1 times. And then you have 2.5 pages of pretty intense analysis, gives you the result. Okay, and here are the references. And once again, thank you very much for coming to my talk. I'm going to stop sharing and say hello to you and
thank you, Anand.
See if questions. Thank you.
That's an interesting talk. Has lots of information, lots of interconnections, and any questions? We have time for a couple of questions. Are you in Atlanta, Anand?
No, I'm in Johnson City.
Oh, Johnson City.
It's close to Atlanta.
Yeah, I know. Yeah, okay, all right. Okay, yeah. Very nice. Nice to see you too. But
nice to see you, KPS.
Appreciate your talk. Very interesting. Okay, thank you. We have a few minutes to wait, I believe. But if anybody has any questions, please.
Probably we can continue with the next talk.
Okay, we can continue. Okay, very good. Okay, thank you, Anand. Yeah. All right. Our next talk is by Professor Adi Ben Israel. I grew up on Ben Israel and Greville's book on generalized inverses of matrices. And Adi was a good friend of mine too. And he also wrote, I like to do a little bit of publicity of my own work a little bit. Adi also wrote the foreword for my book on generalized inverses over commutative rings. And of course, as I said, I grew up on his book, and of course, also C.R. Rao and S.K. Mitra book on generalized inverses. It's a great pleasure for me to introduce Professor Ben Israel, and he will be talking on matrix volume and its applications. Adi, start, please.
My lecture, Matrix Volume and Application, is dedicated to our great teacher, Professor Rao, on his 100th birthday. I wish Professor Rao many more years of good health and good statistics. The volume of an m by n matrix of rank R is defined as the square root of the sum of squares of the determinant of its maximal non-singular submatrices, and 0 if the matrix is 0. Equivalently, the volume of the matrix A is the product of its positive singular values. Definition 1 applies also to non-numerical matrices such as Jacobian. Y volume, every unit cube in the range of A transpose is mapped by A into a parallelepiped in the range of A of volume vol A. Similarly, every ball of volume 1 in range of A transpose is mapped into an ellipsoid of volume vol A. So every volume that can be approximated by cubes or rectangles or whatever, boxes, therefore is mapped by A into a volume, which is the original volume times the volume of A. Special cases, if we have a non-singular matrix W, the volume of the parallel pipe spanned by its columns is the determinant of W. It is a signed volume because the determinant can be positive or negative. The volume of W is the absolute value of the determinant. If the matrix is of full column rank, then the same parallel pipe, the volume is given by the gram determinant, and the volume of W is equal to the square root of the determinant W transpose W. Now, if a matrix is square, the determinant can be 0, but the volume can be still positive. For example, if you take the 2 by 2 matrix of ones, the determinant, of course, is 0, but the volume is 2, the square root of 4. And in fact, the unit cube in the case of this matrix is just the range of A transpose is just a line, and the unit cube is the unit vector on that line, and it is mapped into a vector twice the length. The minimal norm least square solution, which is the Moore-Penrose inverse of A times the vector, the right-hand side B, is a convex combination of the basic solutions. The basic solutions are when you restrict the equation AX equal B into the maximal non-singular submatrices and the corresponding portion of the right-hand side. The convex weights of this combination are proportional to the determinant square of Aij of a maximal non-singular submatrix. And because the sum of them is just the volume square, this is the weight. And the corresponding result for the Moore-Penrose inverse is that the Moore-Penrose inverse is a convex combination with the same weights of the inverses of the basic matrices, that is non-singular, maximal non-singular submatrices, padded with enough 0 to make this compatible. A full rank factorization of A is CR, where C is the full column rank and R is of full row rank. Example, singular value decomposition, QR, etc. And we have an interesting result that the volume of A is equal to the product of the volume of its factors. So it's the volume of C times the volume of R. This follows directly from definition 1, and in fact, we can use this to prove the equivalence of the two definitions. Both the volume and determinant are best understood in a setting of multilinear algebra. So let V be a finite dimensional linear space over a field F. The exterior or wedge product is an operation from V times V to V that is anti-commutative. The scalar comes out and it is distributed in both variables. Now the kth exterior power of V, denoted wedge KV, is simply the space of all exterior products of K elements from V, and in particular the dimension of wedge K Rn is n choose K. The compound matrix comes next. It is the matrix representing the linear transformation from the exterior, the K exterior product of V to the K exterior product of U. And it is defined by CKA, the linear transformation represented by that matrix, times the exterior product of X1 to XK, equal to the exterior product of AX1 to AXK. So the compound matrix is CKA is M choose K by N choose K, and it is of rank RK, R choose K, and in particular CRA is of rank 1. Now, if A is N by N, then CNA is just the determinant of A, as we can see in this relation that the exterior product of AX1 to AXN is the determinant of A times X1 to Xn. And this is for all n vectors in Rn. If the matrix is m by n of rank R, then the absolute value of CRA is the volume of A. And the same relation for any R vectors has plus minus vol A in front. The
compound matrix allows us to define some intermediate volume. So the K volume will be just the Frobenius norm of CKA, or equivalent in terms of singular values, it is square root of the K symmetric function of the square of the singular values. And these have also interesting volume interpretation, but they are beyond this lecture. Let's look now at the singular value decomposition of A. I write it in minimal form so that 0 singular values will be deleted together with the corresponding columns of U and V. So in particular, U and V are not unitary matrices, but just the columns that correspond to the positive singular values. The columns of U are orthonormal bases of the range of A, etc. The corresponding singular value decomposition for CRA, A is of rank R, is this. The metric CRA, sigma, the metric sigma comes out as the volume of A, a number. The vectors U, the matrices U and V come out as U wedge, V wedge. And these are the exterior products of the columns of the matrices. And they are also the Grassmann or Grassmann-Plicker coordinates of the range of A and the range of A transpose. And now move to the differential geometry of surfaces. This stuff is 200 years old by Gauss, given by Gauss. On the left, we have a part of the XY plane. On the right, we have a part of a surface obtained by mapping XY plane into the surface by the mapping phi. And we define 3 objects, E, F, and G. E is the dot product of the X gradient of phi with itself. G is same for the gradient phi y. And F is the mixed dot product. The first fundamental form of Gauss is the length element, ds, and in fact, ds squared is a quadratic in dx and dy, with E to F gs coefficients. But we are interested here in the area element, dA, and we can write it, we can simplify it as the square root of Eg minus f squared dx dy. And in particular, the area of phi u for any set u on the left is the integral over u of the square root of Eg minus f squared dx dy. And this is due to Gauss. And the connection with the previous, with the present lecture is that the square root Eg minus f squared is the volume of the Jacobian J phi in the background. And to show this, keep the same picture and consider the mapping phi that takes xy into xy and z, which is itself a function small f of xy. The Jacobian is 3 by 2, and there it is, and its columns are phi x and phi y before. Eg minus f squared, if you do the arithmetic, is 1 plus fx squared plus fy squared, and it is just the volume square of the Jacobian using our definition. So we can write dA as the volume of J phi dx dy. So this is for the area element dA, and in general, the area of phi u on the right is an integral over u in the left of that volume times dx dy. So this is the preparation for the change of variable formula in integration. The unit normal at the surface must be perpendicular to phi x and to phi y, and therefore it must be proportional to minus fx, minus fy, and 1. But it is normal, it is unit vector, so we have to divide by the Euclidean norm, and it is just the volume of the Jacobian. So this is the formula for the unit normal. And we get the same formula for an n-dimensional surface. And now we move to change of variables integration. The formula given by Jacobi in 1840. We have an integral over the set phi u of a function capital F. Okay, and instead we sometimes prefer to do the integral over u of a more complicated expression, but it may be actually a simpler integration. So on the right you see the composition of capital F and phi and the absolute value of the determinant of the Jacobian. Now, if u and phi u are in spaces of different dimensions, then we cannot use A because the Jacobian is not square. However, if the Jacobian is a full column rank throughout U, then we can replace the absolute value of the determinant by the volume and get this formula, which is the change of variables formula for integration between spaces of different dimensions. In particular, if m is equal to n, and I should add that the Jacobian is non-singular, then the volume is just the absolute value of the determinant, and B reduces to A. Okay, here is an illustration. I have to integrate a function capital F on the surface S, and in particular on a portion phi u. And this integral is the same as the integral over u below of the function, and now the function does not mention z. Instead of z, we have fxy, and we have the volume of the Jacobian is 1 plus fx squared, square root of 1 plus fx squared plus fy squared. When we have a vector field and we want to integrate it over the surface S, the same formula gives us integral over S of f ds, and on the right you have the integral over u, and here we have the inner product of f and the unit normal to the surface times the volume of the Jacobian times dx dy. And here is a magic trick. The volume is the square root of 1 plus fx squared plus fy squared. The unit normal has the same square root in its denominator, so we get a wonderful cancellation, and the integral of f ds over s is the integral over u of a simpler expression, and the square root disappeared. Application to probability. Let x1 to xn be random variables with a joint density f of x, fx. H from Rn to R, a well-behaved function. In particular, it must depend on some of the variables. So we assume that dh, dxn, the partial of h with respect to xn, one of the variables, call it xn, is not 0. And it is required to find the density of the random variable y, which is h of x1 to xn. So we solve for the variable xn in terms of y, and we call this h inverse. So xn is h inverse of y given all the other x's. Change variables from x1 xn to x1 xn minus 1y, so we'll still have n variables, and calculate the determinant of the Jacobian, and it is the partial of h inverse with respect to y. The Jacobian has the first n minus 1 rows, the same as the identity matrix. So the determinant is just the bottom right element, which is partial of h inverse dy. And we can write the density of y using the Jacobi formula. So it is the integral over the variables x1 to xn minus 1. And we have the determinant of the Jacobian. Alternatively, we can structure our variables differently we can say that x1 to xn will be phi of x1 to xn minus 1, and the function phi is x1 to xn minus 1, followed by xn, which is h inverse of y x1 xn minus 1. Then the surface integral of the density of x over vy is the surface where the random variable y gets the value small y. So the integral of fx over that surface is then using the volume expression, the integral of fx, the density of x, times the volume of the Jacobian, times dx1 dxn minus 1. And here we have a nice result that if the ratio of the two scales we used, one of them was the partial of h inverse with respect to y, and the other one was the volume of the Jacobian. So if the ratio of these two does not depend on the axis, may depend on y, but not on the axis, then the density of y is that expression, a, comes out of the integral because it does not depend on x, times, and now we have a much simpler expression, the integral of the density of x over the set vy. This is where the random variable y has the value small y. Now, why would this condition be satisfied? Well, it is satisfied for some very useful functions. For example, the linear combination of the variables, the linear combination of the x's, sum of x squared, or the exponential of the sum of the xi's. So for these three functions, perhaps others, we can get very simple expressions for the density of the function of the random variables. Check the condition for the function for the sum of squares. So when y is sum xi squared, we can solve for xn as plus or minus square root of y minus the sum of squares of all the others. And then the partial of this with respect to y is simply plus or minus 1 over 2 the square root. Similarly, the volume of the other Jacobian will be square root of 1 plus the sum of squares of the partial of h inverse with respect to xi. And when we simplify, we get square root of y divided by the same square root. And therefore, the partial of h inverse with respect to y divided by this is simply 1 over 2 square root y. It is independent of the xi's, and therefore the density of some xi squared is expressed in terms of the integral of the density of f with respect to x on the sphere of radius square root of y, because on that sphere the sum of xi squared is equal to y. Okay, this correlates this result, and now let's look at a strange example. I calculate here y is the sum of square of two independent, identically distributed random variables uniform in 0, 1. And here is what the density looks like. It is constant from 0 to 1. And it is, after this, it goes down according to minus arc cosine of 1 over square root y. So it is pi over 4 from 0 to 1. So if we have a conditional density, that is, I add the condition that the value of y must be less than or equal to 1, I get a uniform distribution from 0 to 1, which is very strange. Before I explain this geometrically, my good friend Yishai Weissman from the Technion was moved by this example to calculate this density of y for all n. And in fact, this is the only one that is pathological in this sense. And here is a geometric explanation using the formula. What we do is that we calculate the length of this arc, of this quarter of a circle, and divide by 2. This is by pi over 4. So when y is less than 1, we get the full quarter circle. But when y is greater than 1, then we only get part of the quarter circle, and this is the part that appears in the formula pi over 4 minus the r cosine. Okay, now since the volume was first announced, there are many applications. One is for face recognition, where we have an atlas or album of faces, and we have a new face, and we ask, is it included in the album? And the answer is yes, if the volume of the difference between the new face and one of the faces in the album is less than epsilon, where epsilon is fixed, and not otherwise. And in fact, this method was checked compared with 4 other methods, and it is better when you have little information. So this expresses the green, the accuracy is replaced by the green line. There are other applications, and I listed here some of them. I also have a bibliography that consists of 100 plus items, some with PDF links and other links. And if you are interested, please let me know, and I'll send you the full slides of this lecture with the bibliography and some other stuff I could not cover in the allotted time. Thank you for your attention.
Thank you, Professor Ben Israel. It's nice to see you, of course.
Yeah, he is as young as he was.
Yeah.
No change.
It's very nice to see you. And if I remember correctly, at one time, Dr. Prasad and myself, we were also looking at exterior products and, of course, compound matrices. Okay, but the volume itself is an interesting talk. And I also remember attending one of your talks about the face recognition, which was very interesting as an application of this. But I'm sure those who are interested can write to you. We are running out of time a little bit. If it is okay with you, we thank you for your talk. Okay, and
he will be joining us in a group discussion anyway.
Right. Okay. Fantastic. Okay. All right. Can we go to the next talk, Prasad?
Probably Professor Jain did not join us. Am I right? Is he there? Yeah. Anyway, we have his recorded talk. We'll continue with playing that.
All right. Okay. All right. So next talk is by Professor Surinder Jain of Ohio University from Athens, I believe. And S.K. Jain, that's how he is known as. He is famous for his work on rings and non-commutative rings, I believe. And I had the opportunity to work in a field of common interest with S.K. Jain on writing matrices as sums of idempotent matrices. So it gives me a great pleasure to introduce his talk today. And if he comes by, of course, we can see him and talk to him too. Yes, please. You can play it, Prasad. Oh, that's an interesting picture. Yes, continue, please. Yeah.
Ohio. Well, this is my greatest pleasure and honor to be a part of a large group of mathematicians and statisticians whose work has or had been influenced by the everlasting contributions of Professor C.R. Rao, FRS, on the occasion of his 100th birthday. May God bless him with happy, healthy, long life as he has been having. I came in contact with Professor Rao many years ago at ISI Delhi, where he invited me to give a series of lectures on fundamental regular rings and rings satisfying polynomial identities. This was at that time when Professor Rao introduced me to generalized inverses of matrices that are connected with von Neumann, related to, I would say, von Neumann regular rings. Soon, I got deeply interested in the theory and applications of generalized inverses. His book with Mitra was so-called My Bible or Gita. Later, my visits led to the ISI, led to the collaboration with the ISI faculty, including R.B. Bapat, S.K. Mitra, K. Prasad, and others. In fact, at Ohio University, we had the pleasure of hosting Professor Rao for a colloquium talk, again, many years ago. Now I'm going to speak very briefly for a few minutes on some results. I'm going to speak very briefly for a few minutes on some results in stochastic matrices that are based on the results of Sinkhorn, Bapat, Goel, Kwok, Prasad, Tainan, and others. Look at the whiteboard. The first lemma is very well known. If A is a stochastic matrix, then the limit of A to the power n as n goes to infinity is an idempotent. Theorem 1. Let A be a doubly stochastic matrix whose one inverse, that is so-called generalized inverse, equal to some polynomial in A which is non-negative. Then some power of A is identity, is idempotent. Sorry, not identity, is idempotent. I wrote identity. It is idempotent. Theorem 2. Let A be doubly stochastic such that some power of A transpose is a polynomial, non-negative polynomial in A. Then the Dresen inverse AD is non-negative, and again some power of A is idempotent or some positive integer. Complete characterization of such matrices is given, and I refer to the following papers. 1. Bapat, Jain, Prasad, Proceeding of the American Math Society, 1999. 2. Bapat, Jain, Tainan, Linear Algebra Applications, 2004. 3. Peter Flohr on Groups of Idempotent Matrices, Compositio, 1969. Well, on another subject of interest is the decomposition of a stochastic matrix into a product of non-negative idempotent matrices. Well, there's a survey on this subject by Jan and Andre Leroy in the American Math Society Contemporary Math Series, 739. One can go and read. It's an interesting survey on this kind of a topic, and it tells you an example of order 4, matrix of order 4, which cannot be decomposed as the product of stochastic idempotent matrices. So the question remains, what kind of stochastic matrices can be decomposed as a product of idempotent matrices, and so on. This is what my just technical talk. I thank you for listening patiently. Any question, you can email me. My email is, I think, jain@ohio.edu. Thank you.
I still do not see Surendra Jain online. So you can write an email if any of you have any questions. And there are lots of references in the talk. So I think this session is concluded now. And we go to the next session. Prasad, you can take over now. I thank all the speakers for the 4 presentations, and they are extremely interesting presentations. Thank you.
Sorry, I was on mute. We'll come back again within 3 minutes, say by 8:30, for group discussion chaired by Simo Puntanen. Hope that he is here around. Thank you.
I see his name there, so he must be around. Yes. Okay. Fantastic.
Yeah.
All right. Thank you.
Well, I heard that. Good morning, Simo.
Good morning, George, or good afternoon.
Welcome to this group.
This is a reality show.
I saw his presence in the morning, 8 o'clock itself.
Yes. I have been up for some time.
Well, you're 7 hours ahead.
Yes.
Of me.
We start whenever you're ready.
Oh, hello, Augustine.
I now invite Professor George P.H. Stein, Professor Dietrich Roshan, Professor Augustine Markiewicz, Professor Adi Ben Israel, Professor T. Krishna Kumar, Professor T.E.S. Rajan, Professor Anand Godbole to participate in the group meeting. And I also request Professor Simo Puntanen, Tampere University, Finland, to chair the group meeting.
Thank you very much and greetings from Nokia. And I know that much that Dietrich is not available for our group session. But how many of you do I see now? Where is Augustin? Is he? Oh, he is definitely very well visible now. I can't hear you.
Yes, I'm here. Yes.
Okay.
Hello, Simo.
Yes. Okay. I guess we can have a go, and it's really very. This is very strange. I am here in Nokia and I am chairing a session. I have not traveled anywhere, but this is very tiring. I had to wake up at 4 o'clock this morning. I wanted to see the opening session, and because of time difference, that took some effort. But in any case, we have now 25 minutes time. And one thing, let me also give some personal comments, because I see myself there, and when I start admiring myself, I am not in synchron with my speech, which is just what my wife usually says. Anyway, we can now start. So we don't have much time per person, but 2, 3, 4 minutes. Any comments? Whatever comes to your mind that you wish to say about these 2 days events are now welcome. Why don't you, George, have a go?
All right. Can you hear me?
Yes.
And
But
can you see me?
It's better now. Now it's okay.
I'm in the bottom right-hand corner.
Yes, it's okay. Yes.
Okay, and you can hear me.
Yes.
All right. I want to begin by wishing many happy returns to Professor C.R. Rao on his 100th birthday, which was 3 months and a few days ago, on the 10th of September, 2020. We are indebted to you for your encouragement over these years of our research in matrices and statistics, and for your support of our series of international workshops on matrices and statistics. In fact, the current terminology is due to C.R. Rao. These workshops are currently under the chairmanship of Simo Puntanen, who is over there in the top left-hand corner with a whole bunch of books, which makes him wondering how many of those you've read. Meanwhile, George and Evelyn Stein thank Professor Rao again for the invitation to visit the Indian Statistical Institute Delhi Center, as it then was, and to stay in house in February, March of 1976. We recall this visit, our first visit to India, with great fondness. Many thanks go to Manjunatha Prasad Karantha for the invitation to speak at this virtual ALAPS 2020 meeting, my first virtual conference, and so I don't quite know why I'm in the bottom right-hand corner. I would have thought if it was my first conference, I should be elsewhere, but anyway, there I am, next to Augie and Godboli and Adi and Simo. And what happened to Jeff? Jeff is over here with his initials, but his face has disappeared. Never mind. We continue that I must thank
the collaborators, my two former students, Karl Chu and Simo Puntanen, for the talk and the work on the talk, When Math Meets Art, with postage stamps and magic squares, that you heard and watched a couple of hours ago, I guess an hour and a half ago. And I want to also thank very much to Awani Kumar, the Indian Forest Service in Lucknow, for his substantial help with Knight's tours. I think almost all the Knight's tours in our talk are due to him. In fact, the day after the overheads the talk was recorded on September 10, September 11, I received an email from Awani Kumar with a Knight's tour on the forest chess board. This is a Russian chess board, which, as far as I know, has not appeared on a postage stamp or philatelic item, but I had asked him for it. It came in the meantime, and it will, I hope, appear in the e-souvenir booklet. Okay, that's it. All right, Simo?
Thank you very much. Thank you very much for your earlier half an hour talk. That was really, really most enjoyable. Thank you very much indeed. Thank you. So we move on. Adi, we were in Hyderabad together 20 years ago when Sierra was only 80 years old. You remember those days?
I believe it was the 75th birthday in Hyderabad. It was in 95.
2000.
It was 2000, okay. So anyway, I expect to be invited again in 20 years for his 120th birthday.
No worries.
And so thank you very much. Thank the organizer. I'm glad to see so many old friends, I mean old young friends. And my path crossed that of the great Sierra because we both wrote books on generalized inverses. His book with Mitra, with the late Sujit Kumar Mitra, appeared in 1971. Our book was supposed to appear about the same time, except for a strange turn of events, that I wrote the book together with my old pal, Tom Greville. We had adjacent offices in the Sterling Hall in the University of Wisconsin in Madison. And on August 70, when we were about to send our book to the publisher, the terrorists blew up the building. They killed one person, a postdoc. They injured some others. But the impact on us was that our two offices that were joint were destroyed. We didn't have any backup material, so all our work about the book was destroyed. And the book was therefore delayed for 3 years. This gave us time to, meantime we had the benefit of Rao Mitra book, and we looked at it and we said that there's nothing we can add statistically, so we avoided statistics altogether on our book. And because we had a benefit of looking at their book, and their book covered statistics admirably. The second edition of our book, this I wrote alone because Greville was already passed away 10 years later. In the second book, I added a short section on the linear statistical model. So in a way, we gave statistics to the great Rao, recognized our shortcomings. And I cannot tell you how much I appreciate all I learned from Rao, directly or indirectly. He is a great man and deserves our admiration.
Thank you very much, Adi. That was interesting. I can tell the following. You visited Tampere, was it 2008 or something?
Yes, that's right.
And you came to my office and you saw the first edition of your book there. And then you said that you have run out of you have no the first edition anymore. And you asked, can you do I accept the second edition and give him the first edition? So that took place. That was very nice.
I have it. This was a good exchange, and if you want it back, I'll give it to you.
Yes, no worries. I'm very happy. Oh, I had a lot of markings, all kinds of marking. I have been reading it quite a lot. Indeed.
Okay, I'll send it back to you. Thank you very much.
No worries. No worries. Okay, Augustine, you are the screen is now yours. Is that all right?
Okay, could it be? Thank you very much, Simo. And first, I would like to say that I really regret that we stopped our plan with Simo to go to India. We started, it was beginning of this year. We have very nice project, but unfortunately it is cancelled. But we have very nice experience to this online conference. And I would like to say that it was also very good. I would like to say something about the organization. That it was very good idea to, for example, record in advance some of presentations, because sometimes it happens that the connection is not very good. And so it is very nice idea. And I would like to also say that raw works was very important for me and stimulated my research. But I was telling about the paper by Rao, published in Annals in 1976. It was in fact the first serious paper I was studying, and I was studying it for a very long time. But the second one was also very important book. It was a book by Rao, linear statistical inference and its applications. And at this time, I'm talking about late 70s or 80s, it was quite hard to get original books. And fortunately, this book was translated into Polish, and it was almost everybody working in the linear model or experimental designs was really using this book, and we are studying. And what was also quite interesting is that always we can finding something interesting. So it was covering quite large area of topics on linear statistical inference. So, and I am also very happy to can see you, for example, George, very to can meet. So it is. I think that for the future we can probably keep such hybrid conferences. That I hope that most participants we can have on plate, but it is good opportunity for those who cannot travel. But of course, we can feel the lack of such personal meetings. For example, with George, some gourmet dinner and so on, and our discussion after the conference. So I hope that quite soon it will be possible. Maybe next year in Manipur. I'm talking about international workshop of matrices and statistics that is planned to be held next year. So thank you very much. And
okay, thank you very much, Augustine. Professor Godball, would you be willing to say something that comes to your mind?
Definitely. It has been a long time since I was at ISI. This was around the time that Professor Raghavan, who's in the picture, was visiting from the University of Illinois at Chicago. And this was 1975. And it was a new campus. The Delhi Center was very new. It had just been built. And it was in the middle of almost a vast, I don't want to call it a jungle, but it was a very remote part of Delhi near the Qutub Minar. And what made it so incredible of a place was that we had so many luminaries. We had Professor C.R. Rao. I mean, his office was right there. It was my dorm room was up on the second floor, and he was on the first floor. That was where his office was. And it was an incredible place in the sense of having so many people who I learned from and who I looked up to. And even though now I've moved away from statistics quite significantly, I was just looking around my bookshelf and I find that one of the few books that I have left that I carry around, it's tattered and it's completely torn and the covers are frayed, but it is something that I still go to with great pleasure to look up things. And recently I was looking at generalized inverses, actually, as a matter of fact. So yeah, it was a great period of time. I must admit, I was a little bit scared of Dr. Rao. But then once he started talking to me, I realized that he was a very humble person at that time. You know, we'd talk about, my father was born actually in 1920 also. And when he visited the ISI Delhi Center, the two of them met and they talked, and it was really a great time. Anyway, so happy birthday, Professor Rao. Thank you very much.
Thank you very much. That was very nice to hear. Professor Raghavan, would you like to be on the screen?
Yeah. Yes, I am on the screen, I think.
Yes.
Are you able to hear me?
Yes, very well.
Okay. See, in 1962, we joined as graduate students from after doing our MSc in statistics from Madras University. And 62, we were 20 people who joined as graduate students. And Sierra was not there, but that was a time when we had the most outstanding combination of probabilists in the world, I can say. Professor Varadarajan had come, Professor Rangarao was there, Professor K.R. Paksarthi was there, and Professor S.R.S. Varadan. Varadan was just finishing his PhD, and he was submitting the thesis, and we learned virtually everything of analysis, topology, anything and everything. And Professor Rao, I was supposed to work in multivariate statistical analysis. And when I mentioned this, immediately he gave me a copy of a paper by Anderson and Bahadur. And I couldn't understand what is a convex function, what is a convex set. I went and talked to Professor K.R. Parsarthi, who said, don't worry, for the first 6 months, you will not follow anything. You have to unlearn the mathematics which you learned in Presidency College. You have to start all over again. And Professor Varadarajan was itching to teach us linear algebra and covered all of them, or spectral theorem for bounded and unbounded operators, left and right. So they were actually looking for students who would be interested in the field. And at the same time, we were not keen on, myself and T. Parsarthi, we were not keen on directly working in probability theory where they have made a dominant effect. So we want to choose a subject which is different, and we came to statistical decision theory, and Professor Rao said, you study whatever you want, but the first 3 years you don't have to do any research. Be learning, taking courses. And then he was writing also at the same time the book, Linear Statistical Inference. And he would come and then ask suddenly doubts. How do you prove Lyapunov's theorem? We have never heard of a Lyapunov's theorem. How do you prove this? How do you prove that? I'm going to throw you out if you don't understand Lyapunov's theorem. That's the fear he created. At the same time, he imposed on us that we must be learning continuously. That was the situation. 66 we finished, and then I go to England. In 66, he was offered a fellow of he was made the fellow of the Royal Society. So he came to London and asked me to come to London. We go there, and he asked me, do you have a car? I don't have a car. So we both go to the Royal Statistical Society office, and here's the story. He's waiting outside, and there was a lady who wouldn't care for us. And she said, please wait. So we were waiting very, very patiently. After 10 minutes, she comes, and then she asks, can I help you? And he says, my name is C.R. Rao. I have been recently elected a fellow of the Royal Society. I came to pay my dues and fill up some forms. She didn't know what to do. Like that, she ran upstairs and brought the chief librarian of the Royal Society, who profusely apologized. And Professor Rao said, no, she was doing her duty. That is the personality of Professor Rao. And anytime I think about him,
can they see?
I have only emotions. I have only emotions. And he has allowed us, and he also asked me to write the notes on non-negative matrices. And that helped me to work with them. Bapat to finally write on the same thing. And it is all basically showing his compassion, showing the direction. He's not pushing you into anything. Here is the direction. If you want, you can go. That's the kind of person who we are blessed with. And also in 75, when I was in ISI, it's the same thing. He said, teach a course which you like. So I started a course on statistical decision. That's how I picked up Bapan as a graduate student. Giving a proof, copying my notes, he gave his own proof. But that's how we, in a sense, he set up the right kind of atmosphere at both places. And I am so happy that he has crossed 100. And I prostrate before him. That's all I can say. Guru Brahma, Guru Vishnu, Guru Devo Maheshwara, Guru Sakshat Parabrahma. Thank you.
Thank you very much. Very nice, very nice. KPS, Professor KPS, would you like to say a few words?
Yeah, that's nice of you to ask. And Simo, it's nice to see you.
Yes. We have to tell that we have a history together. We met 27 years ago. I have my daughter with me, and my daughter is now 50. She made it 50 this year.
Oh, fantastic.
Your son must be also.
Yes, my son is at Rutgers.
Uh-huh.
My son is Swastik Kopati and he is at Rutgers. He is an associate professor in mathematics and computer science.
Very good.
Oh, yes. Nice to hear that.
Yes, okay. And also, let me see. Tejaswini Rao is online. Simo, can you see? Maybe Professor Rao is also online.
Yeah, they have joined just now.
They have joined just now.
I see.
Yeah. Following this, we'll be having a felicitation function. You are all welcome to join.
Okay.
Yeah. So I would like to mention a few tidbits about Professor Rao. Dr. Rao, we call him, and he is very inspiring. A few words with him actually can make you think. And I was a student in his class, and he taught me matrices. Whatever I learned in matrices is because of him. And he would inspire his first chapter in linear algebra and its applications. The first chapter, I spent hours and hours and days and months trying to work out the problems from there. And it really inspired to think further. Okay, I should say that Dr. Rao is inspiration for many of my works, many of my own research interests. And once actually he came to my house a few times, our house a few times to have a dinner with us. And one of the times he said, I have a paper, can you please refer it? I said, sure. And then we started here, and then I asked, what is it? And then he explained to me, and then I said, oh, is that right? And then we started talking about it, and it resulted in 3 further results, further papers of mine, 3 of them. So in that sense, Dr. Rao is extremely inspiring and always took care of whatever anybody thought, took care of his students and his colleagues and everyone. He paid attention to them and he always encouraged whatever you did. I used to work in measure theory first, and he was he always encouraged to say that go and talk to this person, go and talk to that person, there are things that can be done. And that is how I remember Dr. Rao. And I actually went and saw him about 4 years ago? 3 years ago. 3 years ago. And at his home in Syracuse, in Buffalo. And it was a great experience. And I should say that whenever I'm in front of Dr. Rao, I'm a small child. I'm afraid of him. You know, he was as Raghavan sir says, guru. He was a guru, and I always feel that look, you know so much. You whatever you say, great. You know, that's how I always treated, and our respect for C.R. Rao. And I mean, I should. I have no words to pay my respects to Dr. Rao, and we hope that Dr. Rao will be guiding us for many, many, many more years, and I'm sure of this.
Okay, thank you very much. And I guess that we move on to the next session. Do we consider group meeting closed? If I don't hear anything, I think that I will close this group session. Thank you very much. It was this added nice color to this meeting to see you alive. Thank you very much.
Thank you. Thank you all. Yes.
Okay, please join us for the felicitation function. You put him on. Yeah. First of all, you get them, Professor Rao and his daughter on the screen. Okay, no problem. Okay, but don't miss them. They will not come first, so that I can start welcoming them. Okay.
Yeah, of course.
We have a couple of minutes to start the next event.
For the participation in the My sincere gratitude to all the dignitaries for participating in the meeting. Now, we are in the crucial part of the program, that is, felicitation to Professor Rao. I request Professor K. Manjunatha Prasad to take over.
I have a great pleasure.
My father will be here in 5 minutes. He's just coming.
Yeah, we'll wait.
Hello, Dr. Prasad, Teja,
Yes.
Bala here.
Hi, Bala.
Okay. How are you?
I'm doing okay. Thank you. Yeah. By the way, I attended the inauguration ceremony halfway. I was towards the end. I came in and watched the inauguration function. Yeah.
Thank you.
I'm seeing Teja.
Hi. Hi, Bala.
Romba santosham. I'm so happy. I cannot express my happiness. Great. Really great.
It was Raghavan speaking to you.
Good to see you, Raghavan. You're doing fine? Oh, good. Dr. Rao is here. Yes.
He's cleaning his eyes all the time.
Dr. Prasad, these days, I was suggesting to have the session at 9 o'clock. The reason is these days, Dr. Rao wakes up only around 9:30, 10 o'clock, and then has his breakfast and tea. So Teja and I thought that if we plan it at 9, it will be 10:30 here, and it will be appropriate for him.
Yeah, it's his.
It is because of your effort we had a chance of meeting C.R. Rao on the screen.
Oh, not at
Thanks
all.
a lot.
My pleasure. Yeah.
Felicitation ceremony. Okay. Okay. Here you go. Can you see?
Yes. Oh, there he is.
Can you see him?
Good evening. Yeah.
There.
You could see.
Nana, can you see?
Hello.
Yeah.
Hello.
Yeah.
Hello, Dr.
Hello.
Professor Rao.
I'm Prasad.
Congratulations.
If you remember Mitra, I'm Mitra student and Bhaskar Rao student.
Yeah. See? There is a ceremony going on, Nana, in India.
Oh, I see.
Manipal. It's the international conference there, and it's the last day of the conference, and they're felicitating you. Okay?
What is the ceremony?
He wants to know what is the ceremony.
Yeah, I'll describe. I have a great pleasure in welcoming you, sir, along with your daughter, Tejaswini. In fact, I'm having a big galaxy of your admirer students also and collaborators with me.
Where are you
In
speaking
fact,
from?
I'm with Professor Bapat.
He wants to know where you're speaking from.
Raghavan.
No, Prasad.
Parthasarathi.
Prasad, where are you speaking from?
He wants to know where you're speaking from.
Oh, from Manipal, India.
From Manipal University in India.
Which university?
Manipal.
Oh, nice. Hello.
Yeah, I was in ISI with the KPS Bhaskara Rao.
Thank you very much.
Also with Mitra.
Oh.
Prasad was a student of mine. I am KPS.
KPS, Santanana. KPS, who is talking to you. He's trying to see everyone.
Yes.
I'll bring them in.
Yeah. He's trying to look for them.
Yes. I'll bring them in one by one.
Yes, that's better. Yes.
One by one, you will see them.
Yeah.
First of all, let me list the people who are coming in. All right?
Yeah.
I'm having Bapat, R.B. Bapat. Balakrishnan, you know him very well.
Yeah.
Raghavan and K.R. Parthasarathi, B.L.S. Prakash Rao.
Can we see them or no?
No, I'll bring them in later.
Oh,
they
okay,
will
later.
greet him one by one.
Okay.
Okay. I'm having Ben Israel with me.
See,
Simo
that's
Puntanen, you must be remembering him. And George Stan.
Yeah.
And Augustine Marquez, Anant Godbole. I'm having all this with me. And first of all, I'll request Professor Bapat to felicitate you. Then later, all this will come one by one. Greet you.
So one by one, they will come, Nana, and you will see them.
Professor Bapat, I request you to felicitate him first.
Okay, first of all, I don't want to, I want to say how thrilled and happy we are just to see you online. And we consider really ourselves fortunate, having observed your career over the years and then seeing you just after your 100th birthday. So I gave some informal views this morning and also in a program on 10th September on the actual birthday, we had a small gathering. But today I want to be a little more formal and I want to read out of a citation that we have prepared, the organizing committee has prepared, and it will be delivered to you, sir, personally, very shortly, as soon as possible. So I'm going to read out.
Bapat, Nana. Bapat. He's reading the felicitation.
Felicitation. I'm from ISI Delhi, the student of Professor Raghavan, who will be speaking a little later. Okay, so dear respected Professor Kalyanpudi Radhakrishna Rao, you were born on September 10th, 1920, as 8th child of your parents, C.D. Naidu and Lakshmi Kantamma, at Huvina, Hadagalli. After your high school education and college education at Indian College at Visakhapatnam, you earned MA degree in mathematics at Andhra University in 1940. You visited the Indian Statistical Institute during your job and were impressed.
So he's
by
reading the felicitation. Felicitation, he's reading.
Pursue your career in statistics. You joined Calcutta University and obtained MA degree in statistics honors, first rank, and a gold medal in 1943. In August 1946, you visited England on the invitation of J.C. Trevor to work in the Anthropological Museum and wrote the thesis entitled Statistical Problems of Biological Classifications under the supervision of Ronald Fisher to obtain PhD from Cambridge University in 1948. After returning to India in 1948, you married Bhargavi on 9 September 1948. You then joined Indian Statistical Institute and served at various capacities, leading the institution along with Professor Mahalnobi. During your period in ISI, you have been an inspiring teacher, and about 50 students have completed their PhD under your supervision. You, being a legendary hero in the area of statistics, extended the scope of statistical methods practice and published more than 30 books and more than 370 research papers, and several results bear your name. You received innumerable number of recognitions, including several honorary doctorate degrees, Shanti Swarup Bhatnagar Award, National Medal of Science from USA, Guy Medal in Gold of the Royal Statistical Society, and so on. You were honored by the Indian government with Padma Bhushan in 1968 and Padma Vibhushan in 2001. These are among the very highest civilian awards in India. You are always a great source of and many of the present generation are proud of just informing the younger generation about their understanding of your contribution to the subject. The Center for Advanced Research in Applied Mathematics and Statistics, Manipal Academy of Higher Education, Manipal, of your admirers the world over, decided to gather together at Manipal and plan these meetings, but now we are having it virtually. So we kindly request you to accept the token of our respect. I, in the capacity of chairman of the Scientific Advisory Committee, extend my heartfelt greetings to you, sir, and I wish you a very peaceful and healthy life in the years to come. I think we are really fortunate and we are going to remember this occasion for many years to come in our own life. Thank you.
Thank you, Chapandi. Thank you, Andy.
So there you are. Okay.
Sir, I'll be sending you a memento through Balakrishnan later.
See, that's what they're giving you. See. And then it opens up. It has a photograph of you.
Oh.
See?
Manipal.
Manipal. And then a write-up about you.
Oh. Thank you very much.
Wait, I'll unmute it now.
You're right. I'll call one by one. Okay. I request Professor Balakrishnan to come forward and greet Professor Rao.
Oh, thank you. Oh, thank you very much. First of all, I want to acknowledge that both Dr. Bapat and Dr. Prasad for working tirelessly on putting this program together and also for the organization of the conference and the technical talks. It's a great honor for me and to be associated with this event to honor Professor Rao Like many of you, I also have been in constant admiration of him as a person, as an academic, as a researcher, and what he has contributed in different forms for the profession and life. I met Dr. Rao on a personal note in late 80s when I invited him to come to McMaster on a Britain professorship, which is one of the distinguished professorships available at McMaster University for visiting scientists. And that is the time when I started interacting with him. And since then, we have had a fruitful collaboration for over 3 decades on various projects, research, and also to travel to many conferences together. I still fondly remember his visit to Greece for a conference that I organized at the University of Athens and to France. So it gives me great pleasure to see him, mind being sharp and his health, though frail, is in good shape, and Teja is taking good care of him. And I used to visit him constantly when he is in Buffalo, but due to the pandemic, I have not been able to visit. Hopefully soon. So let me join all of you in congratulating such a glorious academic life with utmost distinction in various forms of academic contributions. Thank you, Dr. Rao, and I wish you many more years in good health. Thank you very much.
Thank you. Thank you, Chapati. Hello. Bala.
Yes. Now I'll request Professor Raghavan to come forward and greet Professor Rao. Raghavan, your student.
So, do you see Raghavan, Nana? Huh? Raghavan. So he talks. Can you get rid of this?
What do you need? Hello?
Bar.
Are you able to see me, Professor Rao?
Nana, Raghavan.
You just talk. If you talk, it'll automatically go to him. Don't mute him.
Test Raghavan. Yes, Raghavan. Are you able to see me, Professor Rao?
Nana. Hello. That's Raghavan, Nana, from Chicago.
Hello.
Yeah.
Hello.
There you go. Right there.
There, yeah.
Say hi. Say hi, Dr. Rao.
How are you? I am in Chicago.
How are you?
Good. I mean, see, 5 years back, I came to see you. But you shaped my career, my life, and everything.
He recognized you.
The thing is, in '62, when we joined as graduate students, we had the best time for academic activity with Varadarajan, with K.R. Patsarathi, S.R.S. Varadan, Rangarao, and all of them. And you used to be constantly coming and going for international trips and things like that. And when I finished my thesis, the very next day you positioned me to George Barnard. And then my visit to meet you at London airport to go and to go to the Royal Society, when you were offered the Fellow of the Royal Society prestigious award. So we both went together to the Royal Society. You may or may not remember now, old age. But those are fond memories. And in '75, when you moved to Delhi, then I was a visiting professor there. You told me to take care of the library and teach whatever I liked. And that's how I picked up Bapat. And that's how we also wrote a book on non-negative matrices, which was also inspired by whatever I was doing earlier and whatever was Thank you. We are very, very happy. I met Mrs. Rao, and Teja. And all I can remember is the mango which we carried. Mrs. Rao ate it well. And those are our memories. I have pictures of them.
Raghavan, yeah.
Yes.
Hello.
Hello.
How are you?
I'm fine. I'm fine. I'm really fine, and this is a unique opportunity for me to see you here.
Now I'll request one more student of yours to come forward. K.R. Parthasarthi. K.R. Parthasarthi, he will be coming on the screen now.
KRP Parthasarthi.
KRP from Delhi.
Delhi Linchi.
I joined the Indian Statistical Institute in 1956, which is the silver jubilee year of the institute. And as a student, I was introduced to many distinguished visitors, starting from Ronald Fisher, Jerzy Neyman, academician Bogolyubov, academician Amundsen, and the Japanese operations research specialist Toshio Kitagawa, and many others. And then that was also the first time I happened to meet Professor Raghuraj Bahadur. And when I started my research, I came to you and asked for a problem, and you told me, learn information theory. At that time, we had a visitor by name Professor Didi Joshi from France, and he will help you.
Become old. Yes, become old.
Professor Joshi left ISI after a short while, and I came to you and said, I am reading a book by the Russian mathematician like Khinchin, and I started reading and began to lecture to you on the same subject in your office. And you, with your constant attention and your mentoring, I could continue to work in. Starting from information theory, I moved to group representations and probability theory on probability on groups under the supervision of V.S. Varadarajan. And much later, you sent me as a visitor to the USSR Academy of Sciences, where I could listen to, I had the pleasure of very wonderful conversations with academician Kolmogorov. It was a great opportunity for me. Then I could make a friendship also with many eminent mathematicians like Professor Gelfand, Dynkin, and many others. It was a wonderful opportunity. And in 1963, I returned from Moscow. I began to take interest in teaching in the RTS. And in 1965, I left for England and joined the University of Sheffield as a lecturer. But I continue to keep in the back of my mind, I always kept the theory of information theory as a whole, in general, all throughout my life. And much later, when I began working in quantum statistics, I found an opportunity to renew my knowledge of information theory, and I wrote a book. This enabled me to write as a tribute to you on your 90th birthday an article on the philosophy of the Khmer Rao bound. And now my joy in seeing you, albeit on the online, my joy knows no bound. Thank you very much.
Thank you, Professor.
Where are you now in Delhi?
Thank you, Professor Parthasarathi.
He's saying, where are you now?
Oh, I am in Delhi. I am in Delhi, even though I am in ISI Delhi, because of COVID, I am imprisoned at home.
How do you get rid of it again? This bar.
Oh, just click out of it. Just click anywhere. There you go.
Okay. Professor Parthasarathi, Professor Parthasarathi, I don't know whether you heard, Dr. Rao was making a comment that he recognized you, but he said that you are looking old.
That's the first thing he said. He's looking old.
Yes.
He remembers you all as his students, you know, young.
Dr. Prasad, may I take a minute? It is something that Teja and I were talking about in September. One of the interesting characteristics of Dr. Rao is his sense of humor. And his sense of humor is not lost. Teja was telling me a story that there was a family party arranged, a small group of people, on his 100th birthday in Buffalo. And of course, for the event, he had to be dressed. He had to be dressed in a suit and a tie, etc. And two helpers who come to help him during the day dressed him up. And he apparently made a comment that what is the special occasion? And they said that you are turning 100 today and we have a party. And he said, I suppose one has to turn 100 to have the pleasure of two women dressing you up.
Yeah, he's in Delhi. He's in Delhi.
That is what is keeping me young.
Yeah.
Thank you.
We all hope to be dressed into by two women.
Where are you now in Delhi?
He's in Delhi, KRP, and this is Prakash Rao. Correct? Yeah. Prakash Rao, KRP. BL is Prakash Rao.
Good evening. Good evening, Dr. Rao.
Where is he?
Hyderabad.
Yeah. This Prakash Rao here. The first
time.
Can you hear me?
Yes.
Yeah. So the first time I met you was in 1960, and I was 18 years old at that time. And it has been a long journey with you, and I enjoy.
Yeah.
So the first time, in fact, Professor K. Nagabhushnam, he gave me a letter when I was selected for MSTAT, and I told him that I was going to Calcutta. So he gave me a letter, and that letter I gave it to you. And since you were a student of Professor Nagabhushnam also, so there, that's the first time I met there. And then, of course, over the years, we have been in touch. And I was your student in MSTAT course. And later on, after I returned to India after my PhD at MSU, you invited me to join ISI, but I went to IIT Kanpur. But then again, it brought me back to you when you moved to ISI Delhi. It was great knowing you over the years, and I learned a lot from you. And I was fortunate to be your student over the years, to be your colleague over the years, and now to be attached to the institute you have established in Hyderabad, and for which I am still connected with this. And I am fortunate. This is one of my greatest blessings from you, and we wish you a very long life. Thank you very much.
Thank you very much.
Thank you.
Thank you, Professor Prakash Rao. Now I'll call upon my guru and your admirer, Bhaskar Rao.
Rao garu. Nenu Bhaskar Rao, KPS Bhaskar Rao and Surekha. You remember?
Yes.
We came 3 years ago and met you in Buffalo.
Yes.
MP Rao, myself, Surekha, and Palanivelu, we came and met you. We always remember you. And in 1966, I came as an MStat student to Calcutta. From that time on, you have been an inspiration. You are an inspiration for this generation and for many more generations. I learned all my linear algebra from you, all of it. And you encouraged my research, and whatever I achieved is because of you. And we hope that you will be an inspiration for us and many more generations for many years to come. And you have left an indelible mark on several of areas of statistics and also several of us. So we thank you, and we need your blessings all the time. Thank you.
Thank you.
Thank you. The world is a better place because of you, Dr. Rao. Thank you so much for what you have taught us, what you have taught everyone. So it's not just your students who were in your room, people who anytime came close, always learned something from you.
Right.
So grateful to you for that. Thank you so much. Thank you.
Thank you very much.
You remember Surekha's Bhaskar Rao, right?
Yeah.
Yes, okay.
Thank you.
Yeah, thank you.
I request Ben Israel to join us and greet you. Ben Israel is your contemporary. He also wrote Generalized Inverse book when you wrote book on Generalized Inverse.
Professor Rao, it's a great honor to be on your birthday party.
Ben Israel, your video is not on.
Am I on now?
Yes.
Ah, fine.
Okay. Professor Rao, we thank you very much for all you did for the research and for the teaching and for the profession in general. Your name is in stone all over the world, and we all admire and love you very much. Thank you for everything you did.
Thank you.
Thank you.
Now we have your great admirer, Simo Puntanan. with us.
Good afternoon, Professor Rao. Very happy. Simo Puntanen from Finland. Small Nordic country between Sweden and the former Soviet Union, nowadays Russia. I wish you very happy centenary, and you have been a really great source of inspiration for so many years. And tomorrow I will show 100 photos of you. Thank you very much.
Thank you.
Thank you.
We have one more friend of yours, that is Professor Stan. George Stan, you may be remembering.
We haven't seen him in a long time.
Canada.
Oh, hi. Nana, look at Professor Stein. Professor Stein from Montreal.
Oh, yeah.
Professor Stan, you are muted. Please unmute.
Oh my God. His wife used to look like Audrey.
Hello.
Professor Stan, please unmute yourself.
Hello, how are you?
George, your microphone has to be turned on. You are muted. Can you click on your microphone and turn it on, please?
Unmuting.
Now you are okay. Go ahead.
Now I'm okay. But I could hear you, Bala. You could not hear me.
Yeah, thank you.
But now you can hear. Teja, you hear me? Hello, Teja.
Yes. Hi, Professor Stein. Lovely to see you.
Lovely to see you too. It has been 40 years since I last saw you.
Yes.
Amazing. So, if it weren't for you, CR, I would never have met your daughter. And that was in 1976, in March, February of 1976, 44 years ago. So you were 56 then, and I was 39 or something like that. Anyway, I wish you a very happy birthday, many happy returns, and many thanks for your invitation at that time. Hi, Teja. Bye.
How are you doing?
Oh, hanging in there. How are you doing?
I remember my father used to call your wife Audrey Hepburn. Do you remember that? When you were in Calcutta? He can't hear me.
I can hear you, but it's sort of not clear.
It's not clear, yeah. You're still in Montreal, right?
Yes, right now in Montreal.
Okay.
And you are still in Buffalo?
Yes, yes.
Thank you very much.
Okay. Thank you, Professor Stan.
Oh, Montreal.
Yeah, yeah. And
we have another admirer of you from Poland, Augustine Markiewicz.
From Poland?
Poland, yeah.
I've been there?
Yes, I'm here. I am very happy to see Professor Rao. And
here he is. He's over here.
Because last time we have Professor Rao was visiting Poznan when in 1991, and he was getting when you were getting a honorary degree from Adam Mickiewicz University. You were invited by, for example, Professor Caliński and Professor Baksalary, and I was big pleasure to collaborate with you, maybe not directly, but through Professor Baksalary. And and I am co-author of 2 papers. And I would like to send you my best wishes for your birthday, and to wish you many more anniversaries to come. And I would like to express my gratitude to your work, who was greatly influenced to my research. And my research was, I presented today in my talk, one of field of my research that was inspired by your paper, Annals, 1976, and it was the admissibility problem. I was working quite a long time, and I will also mention about your book on linear statistical inference and application. And this book was translated into Polish, and it was very important book for. In the 80s, everybody was very happy to can have this book, because at this time it was quite difficult to get original book in your original book in English. Fortunately, we had this translation. And I can mention also another book by Rao Mitra about generalized inverses. So I am very happy to can see you and happy to can attend this conference. And I would like to send the best wishes from Poland, from Professor Caliński and from our Department of Mathematical and Statistical Method from Poznań University of Life Sciences. It was former Academy of Agriculture, and my advisor was Professor Baksalari, who was visiting you several times in USA, and
muted.
Thank you.
Thank you. We have TSS RK Rao with you. TSS RK Rao, please bring in. You must have met TSS RK Rao at Bangalore.
He's from Bangalore,
TSS,
Nana.
you are muted. Please unmute.
Yeah. Namaskaram, Andy. I am TSS RK Rao. I retired as head of the Bangalore Center of ISI. And the enormous influence of yours on the Indian Statistical Institute has really guided us through all the years. Today is the
Bangalore
Foundation Day of ISI. I'm able to meet you on this day.
Dad is able to read. I'm not able to read the notes.
Thank you.
Thank you.
Okay, fine. Sir, I know we are troubling you. You have taken lots of pain to join us. And you are a great source of inspiration. And we look for your blessing forever.
Say thank you very much, Nana.
Thank you very much.
I request Professor Balakrishnan to give a vote of thanks on behalf of our entire committees, organizing committees.
Thank you.
Thank you very much, Dr. Prasad. It was a great pleasure to see all my good friends over the years to take part in this event, to felicitate Professor Rao on this special occasion. The fact that many researchers from different parts of the world coming together to show their appreciation gives a clear impression on what kind of impact Professor Rao has had on the scientific community. So thank you all, one and all, for taking part in this event. And special thanks go to Teja for arranging Professor Rao to appear in person so that we can all see and listen to him. So thank you very much.
Sure, for getting him ready.
Yeah.
Thank you.
While winding up, we'll play a few messages. Thanks a lot.
So a recording of this will be available, right?
Yes. Yeah, we'll make it available. We'll send you the link. It will also be available in the YouTube.
Okay. because I would like to put all of this in his gallery in the institute.
Sure.
So I'll thank you. Thank you for doing this. It was really special.
Thank you.
Thanks a lot for joining us.
Both of you keep well. All of you keep well.
too. All of you too.
Okay. Bye.
Bye.
Thank you.
Nice.
Bye.
Rao.
Thank you, Prasad, for organizing this. You've done a remarkable job.
Thank you,
You've done
madam.
a wonderful job and very good to see you after so many years. Very happy to do that. And wish you all the best for everything that you do. And we hope we can meet you sometime. Thank you.
Sure.
Keep up the great work. Keep up the good work. You've done amazingly well. Absolutely amazing. Thank you. Thank you, Prasad. All the best to you. And thank you, Teja, for bringing Dr. Rao. Such an honor. Nice meeting you, Dr. Raghavan. Is there? Yeah. Okay. We can. Yes.
Currently, I'm head of India Statistical Institute Delhi Center, and I'm glad to be the part of this celebration, Professor Rao. At ISI Delhi Center, that it was initially that I'll say that he was associated very much with the development for the structures of the buildings, as the architects of different courses, and to be organized at Indian Statistical Institute Delhi Center. And as it is evident from these photographs that you can see that I'm playing some of the photographs taken during inauguration. That the center at that time it was inaugurated by Srimati Indira Gandhi, and you can see that he is giving inaugural address during the celebration, and along with him there are other dignitaries, and so these are the very rare photographs that which you can see here, and time to time I have met him when he used to visit ISI Delhi Center. I had several that informal talk with him, and he used to ask us that what are the activities going on, and the center, and he used to guide us that what are the activities we should look in the future. And one thing I must mention, that when he used to give talk, so that used to be accessible even to the non-specialist. So thank you.
Department of Mathematics, Manipal Institute of Technology, Manipal, is privileged to be part of CARMS in organizing the International Conference on Applied Linear Algebra, Probability and Statistics to honor Professor C.R. Rao during his birth centenary year. An eminent statistician and a living legend, Professor Kalyampudi Radhakrishna Rao, popularly known as Professor C.R. Rao, is a true source of inspiration to every statistician. His works on estimation and statistical inference, design of experiments, and multivariate analysis using the concepts of linear algebra and matrix theory is beautifully illustrated in his book, Linear Statistical Inference and Its Applications, which is a ready reckoner to every statistician. Padma Vibhushan and Bhatnagar awardee, Professor C.R. Rao is well known for Kramer-Rao bound, Rao-Blackwell theorem, orthogonal arrays, and the score test. His book, Statistics and Truth, Putting Chance to Work is something to be read by every mathematician and every statistician. It has far implications of statistics in various fields such as economics, genetics, anthropology, geology, national planning, demography, biometry, and medicine. I conclude by quoting the worthy quotes from his book, Statistics and Truth, Putting Chance to Work. Uncertain knowledge plus knowledge of the amount of uncertainty in it is equal to useful knowledge. He who accepts statistics indiscriminately will often be duped unnecessarily. But he who distrusts statistics indiscriminately will often be ignorant unnecessarily. Sir, the work that you had carried out those days is finding its wide applications now. May it be in machine learning, deep learning, or artificial intelligence. I, along with everyone from the Department of Mathematics, MIT Manipal, wish you a very happy birthday on this occasion. May Almighty keep you in good health. Thank you.
Greetings from the Department of Data Science, Prasanna School of Public Health. I consider it a privilege to be a part of the International Conference on Applied Linear Algebra, Probability and Statistics, organized by the Center for Advanced Research in Applied Mathematics and Statistics, MAHE, in association with the Department of Data Science, MAHE, Department of Mathematics, MIT, MAHE, Department of Mathematics, SMIT, Sikkim, and Indian Statistical Institute, Delhi. This two-day event is indeed a special one for all of us, as we have virtually gathered here to be inspired by the life and research of Padma Vibhushan, Professor C.R. Rao, as we celebrate his birth centenary year. The contribution of Professor Rao to mathematical science is so immense that student community across the world begin their journey with a few of the several textbooks authored by the legend. Sir, turning 100 is the biggest milestone birthday. We pray to the Almighty to bless you with happiness, warmth, and health. May you continue to enjoy the journey of life. I understand that many of his great students, collaborators, and his admirers across the world are expected to take part, share their thoughts on Professor Rao, and knowledge to celebrate the occasion, inspiring the young minds participating in the conference. It is fascinating to note that this virtual conference is truly going to evolve as a platform for intellectual discussions on topics relevant to us today. I truly believe that this event will enlighten our intellectual spirits as we walk past a year of the pandemic. On behalf of the Department of Data Science and my behalf, I extend my best wishes to this initiative. We look forward to being academically illuminated and motivated to make contribution to the treasure trove of knowledge. Thank you.
Thank you, madam. I sincerely thank everyone who joined us today with the information that tomorrow morning we'll start at 8:30 sharply with a group meeting chaired by Professor Jeff Hunter. Thank you again. Bye.